Hey everyone, before we dive into the mind-bending world of reality, comment down below where are you watching this video from and what time is it where you are. Maybe you're at home, chilling on your couch, or perhaps you're out and about, maybe even stuck in traffic. Wherever you are, take a moment to really feel it. The solid ground beneath your feet, the air on your skin, the sounds around you. This, you might think, is reality. But what if I told you that the very fabric of this reality, the world you're experiencing right now, is far more complex, more bizarre, and infinitely more mind-blowing than you could possibly imagine? What if everything you perceive is just a tiny, incredibly intricate piece of a much larger puzzle? Join us on an extraordinary journey as we peel back the layers of existence, from the unbelievably small to the unimaginably vast. We're going to explore the hidden truths of the universe, challenge everything you thought you knew, and ask the ultimate question: what is reality, truly, and what's your place in it? For centuries, philosophers and scientists alike have grappled with perhaps the most fundamental question imaginable: what is real? And perhaps even more importantly, how do we know it's real? You might be listening to this audiobook in your home, on a walk, or perhaps during your commute. You're hearing my voice, feeling the device in your hand, seeing the world around you. This, you might think, is reality. Solid, tangible, undeniably present. But what if I told you that even this seemingly straightforward reality, the one we navigate every single day, is far more intricate, more deceptive, and ultimately more astonishing than you could possibly imagine? Let's begin with the utterly mundane. Consider a simple object in your immediate vicinity. Perhaps a coffee mug, a book, or even the wall before you. You perceive its color, its shape, its texture. You can touch it, feel its temperature, maybe even smell it if it's something like fresh coffee. This is your primary interaction with what we commonly call reality. It feels so robust, so unquestionable. If I were to ask you to describe that coffee mug, you'd probably tell me it's ceramic, white, cylindrical, and holds liquid. These are observations, direct experiences relayed through your senses. And for 99.9% of our lives, this level of understanding serves us perfectly well. We navigate traffic, prepare meals, hold conversations, all based on this intuitive classical understanding of a solid, predictable world. The sun rises in the east, gravity keeps our feet on the ground, and dropping an apple means it falls. Simple, obvious, real. But what if we start to peel back the layers, just a little? Let's take that coffee mug again. You see it as white, but is it inherently white? Or is its whiteness a product of how light interacts with its surface, and how your eyes and brain interpret that interaction? If you were in a room lit by only red light, that white mug would appear very different, perhaps reddish or dull gray. The mug itself hasn't changed, but your perception of its color has. This isn't a trick of the light. It's a fundamental aspect of how our sensory apparatus constructs the world around us. Our eyes are equipped with specialized cells, rods and cones that detect specific wavelengths of light. Our brains then take these electrical signals and translate them into the rich tapestry of color we experience. A bee, for example, perceives ultraviolet light, seeing patterns on flowers that are invisible to us. Is the bee's reality of that flower more real than ours, or simply different? This immediately introduces the idea that our perception is not a direct window to an objective reality, but rather an intricate interpretation of signals. Consider sound. You hear my voice now. It's not actually my voice traveling directly into your ear. It's vibrations in the air, pressure waves that are then converted into mechanical vibrations in your eardrum, then into electrical signals by tiny hair cells in your inner ear, and finally, processed by your brain into the recognizable sound of a human voice. If there were no ear to detect those vibrations, would the sound exist? A tree falling in a forest, proverbially, does not make a sound if no one is there to hear it. It merely creates air disturbances. The sound is a creation of a conscious observer. This isn't just semantic hair-splitting. It's a crucial insight into how much of our perceived reality is in fact a construct of our own biological machinery. And what about touch? When you feel the smooth surface of that mug, you're not actually touching it in a literal sense. At the atomic level, the mug is composed of atoms, and so is your finger. These atoms are mostly empty space, with a tiny nucleus surrounded by a cloud of electrons. When you touch the mug, what you're experiencing is the electromagnetic repulsion between the electrons in your finger and the electrons in the mug. They never actually make direct contact. It's like trying to push two strong magnets together. They repel each other before they ever truly touch. So the sensation of solidity is an illusion born from fundamental forces and the incredible speed at which our brains process these interactions. The mug feels solid because the forces preventing your atoms from interpenetrating the mug's atoms are immensely strong, creating a resistance we interpret as solidity. This means that what we perceive as a dense, impenetrable object is at a more fundamental level, a bustling, energetic dance of particles, mostly empty space, held together by invisible forces. The very ground beneath your feet, the chair you sit on, even your own body, all are vibrating fields of energy, not solid objects in the way our everyday experience suggests. This leads us to the concept of subjective reality versus objective reality. Our senses, our brains, and even our past experiences and beliefs all contribute to our subjective reality, the world as we perceive it. Think about eyewitness testimony at a crime scene. 10 different people can witness the exact same event and provide 10 slightly different accounts, not because they're lying, but because their individual perspectives, attention, and interpretations of events create unique subjective realities of that moment. Our emotions, our hunger, our fatigue, even our cultural background can dramatically alter how we interpret the world around us. A delicious meal to one person might be unappetizing to another. A piece of art that moves one person to tears might leave another utterly indifferent. These are not just matters of taste, they are demonstrations of how profoundly our internal states shape our external perceptions. But if our reality is so subjective, is there an underlying objective reality that exists independently of any observer? This is the bedrock of scientific inquiry. Science strives to discover truths about the universe that are universal, reproducible, and verifiable, regardless of who is observing them. When a physicist measures the speed of light, or a chemist identifies a specific element, they are attempting to isolate and quantify aspects of an objective reality that would exist even if humanity vanished tomorrow. The laws of physics, the fundamental constants of the universe, these are believed to operate universally, whether or not a conscious mind is there to witness them. However, even within science, the very act of observation sometimes plays a peculiar role, as we will explore in later chapters when we delve into the mind-bending world of quantum mechanics. For now, it's enough to acknowledge that while our individual perceptions are unique, there is a scientific pursuit of universal principles that govern the cosmos. The historical journey of understanding reality is a fascinating one, marked by profound shifts in perspective. For millennia, humanity largely relied on myth, religion, and philosophy to explain the world. The heavens were a divine realm, lightning bolts were the wrath of gods, and the earth was the unmoving center of the universe. Then came the scientific revolution, a monumental turning point where observation, experimentation, and logical reasoning began to take precedence. Figures like Galileo, Copernicus, and Newton challenged established dogma, showing that the universe operated according to discernible, predictable laws. The Earth orbited the Sun, objects fell due to a universal force called gravity, and the motion of planets could be precisely calculated. This ushered in an era of classical physics, a period where reality felt solid, deterministic, and entirely comprehensible. It was a universe like a grand clockwork mechanism, with every gear and spring meticulously laid out, its future entirely predictable, if only we knew its present state precisely enough. This classical worldview, the one that governs our everyday experience of coffee mugs and falling apples, has been incredibly successful in building our modern world, from bridges and airplanes to computers and satellites. It's the reality that allows you to confidently step out of your door without worrying about suddenly floating off into space or walking through a wall. However, as scientific instruments became more sophisticated and our inquiries pushed into the extremes, the very small, the very fast, and the very massive, this comforting classical picture began to unravel. The simple, intuitive rules that govern the billiard balls of our macroscopic world ceased to apply. At the turn of the 20th century, two revolutionary theories emerged that would fundamentally reshape our understanding of reality, shattering the classical clockwork universe and ushering in an era of profound mystery and wonder. These were quantum mechanics, dealing with the incredibly tiny building blocks of matter and energy, and Einstein's theories of relativity, which redefined space, time, gravity, and the very fabric of the cosmos. These theories, though initially counterintuitive, have been repeatedly confirmed by countless experiments, forming the bedrock of modern physics. They reveal a universe far stranger, more dynamic, and arguably more beautiful than our everyday senses could ever convey. So when we talk about the different realities of the universe, we aren't talking about something out of a science fiction movie, though science fiction often draws inspiration from these ideas. We are talking about the scientifically discovered layers of existence that lie beneath, alongside, and perhaps even beyond the familiar world we experience. We are talking about the reality revealed by probing atoms, by observing distant galaxies, by contemplating the very nature of space and time. We are acknowledging that our everyday perception is a highly specialized, evolutionarily refined filter, designed for survival on a specific planet, at a specific scale. It's an incredible filter, incredibly effective for its purpose, but it masks a deeper, more profound truth about what constitutes reality. The purpose of this audiobook is to guide you, step by step, through these different layers. We will move from the reality of our senses to the bizarre realm of the quantum, from the bending of space-time to the mind-boggling possibility of multiple universes. We will explore how our own consciousness might be intimately connected to these deeper realities and ponder the ultimate questions about existence. We'll attempt to demystify complex scientific concepts using relatable analogies and clear language without oversimplifying to the point of inaccuracy. This isn't a textbook, it's an exploration, an invitation to expand your understanding of what's truly possible. As we progress, you might find some of these concepts challenging to grasp, as they often defy our common sense intuitions. That's perfectly normal. Our brains evolved to navigate a medium-sized world, at medium speeds, under medium gravity. The extremes of the universe, the incredibly small, the incredibly fast, the incredibly vast, demand a new way of thinking, a willingness to let go of preconceived notions about how things should work. But the reward is immense, a glimpse into the true majesty and mystery of the cosmos, and a profound appreciation for the intricate dance of forces and phenomena that make up everything. In this first chapter, we've merely scratched the surface, establishing the premise that our everyday reality is not as simple as it seems. We've touched upon the role of our senses in constructing our subjective world and the scientific quest for an objective understanding. We've hinted at the limitations of classical physics and the revolutionary ideas that emerged in the 20th century. With this foundation laid, we are now ready to dive headfirst into the truly strange and fascinating world of the quantum, where the very solidity of matter dissolves and reality itself seems to engage in a cosmic game of hide and seek. Prepare to have your assumptions challenged, your curiosity ignited, and your understanding of reality fundamentally transformed. The journey is just beginning. Our journey inward into the very fundamental nature of existence now leads us to the most perplexing and counterintuitive realm known to science, the quantum world. Having peeled back the layers of our everyday, macroscopic reality to reveal its underlying energetic and probabilistic nature, we must now shrink our perspective beyond the atomic into the domain of subatomic particles, electrons, photons, quarks, and the other minuscule entities that are the true building blocks of everything we perceive. It is here, at scales so infinitesimally small, that our classical intuitions utterly fail, that reality itself undergoes a profound and bewildering transformation. The universe, at its most fundamental level, operates under rules so alien that they force us to reconsider everything we thought we knew about matter, energy, cause and effect. The classical physics that so elegantly describes the flight of a baseball or the orbit of a planet finds itself entirely inadequate when confronted with the bizarre behavior of particles at the quantum scale. For centuries, our understanding of the physical world was rooted in certainty and predictability. If you knew the initial conditions of a system, the precise position and momentum of every particle, you could, in principle, predict its entire future. This was the deterministic worldview of Isaac Newton, a universe like a perfectly calibrated clockwork mechanism. But as the 20th century dawned, scientists began to probe the atom with increasing precision, and what they found defied every expectation, shattering the comforting illusion of a predictable universe. One of the most foundational and utterly mind-bending discoveries was that of wave-particle duality. Consider light. Is it a wave, like the ripples expanding across a pond? Or is it a stream of discrete particles, like tiny bullets fired from a gun? For decades, this was a fierce debate. Experiments, depending on their setup, seemed to conclusively prove both: the phenomenon of diffraction, where light bends around corners, or interference, where light waves combine to create patterns of bright and dark, unequivocally pointed to light behaving as a wave. Yet the photoelectric effect, where light ejects electrons from a metal surface, could only be explained if light consisted of tiny packets of energy, which we now call photons, essentially particles. So what is light really? The answer, incredibly, is both, or, perhaps more accurately, neither in the classical sense, but rather a hybrid entity that exhibits wave-like properties in some situations and particle-like properties in others. It's as if a fish could suddenly sprout legs and walk on land when observed in one context, and then swim gracefully through water when observed in another, without ever truly being just a fish or just a land animal. This duality extends beyond light to all matter, including electrons, protons, and even entire atoms. The most famous illustration of this paradox is the double-slit experiment, which we hinted at in the previous chapter, but which warrants a much deeper exploration here, due to its central importance in revealing quantum weirdness. Imagine setting up a screen with two very narrow parallel slits, and behind it, a detector screen to record where particles land. Now, let's fire a beam of electrons, one at a time, at this barrier. If electrons were tiny, classical particles, like miniature golf balls, you would expect them to either go through the left slit or the right slit, creating two distinct bands of hits on the detector screen, directly behind each slit. This is precisely what happens if you fire larger objects, like paintballs, at a similar setup. However, when you actually perform the experiment with electrons, something utterly astonishing occurs. Instead of two bands, you observe an interference pattern on the detector screen, a series of alternating bright and dark bands, just like what you'd get if two waves were interfering with each other, reinforcing in some places and cancelling out in others. This pattern is the hallmark of wave behavior. How can a single electron, fired one at a time, create an interference pattern? For waves to interfere, they must somehow overlap. It implies that each individual electron, acting as a wave, simultaneously passes through both slits, interferes with itself, and then collapses into a particle-like hit on the detector screen. This isn't just baffling. It challenges our deepest intuitions about individuality and locality. An electron, it seems, doesn't have a definite path until it's observed. But the weirdness intensifies. What happens if you try to figure out which slit the electron actually goes through? What if you place a tiny detector or a light source near one of the slits to observe its path? The moment you introduce an observation, the interference pattern vanishes. The electrons suddenly behave like classical particles, producing two distinct bands on the screen. It's as if the act of looking at the electron forces it to choose a single path. This phenomenon is known as the observer effect, and it's not about consciousness in a mystical sense, but rather about the inevitable interaction of the measurement device with the quantum system. Any attempt to gain information about the particle's path inherently disturbs the system, forcing it to relinquish its wave-like, probabilistic nature and adopt a definite particle-like state. It's a profound statement. What we observe is not necessarily what is prior to observation. The very act of measurement seems to play an active role in shaping the reality of the quantum world. This leads us to the concept of superposition. Before a quantum particle is observed or measured, it doesn't exist in a single definite state. Instead, it exists in a superposition of all possible states simultaneously. Imagine a spinning coin in mid-air. Before it lands, It's neither heads nor tails. It's a superposition of both. Only when it lands and we observe it does it collapse into a definite state, either heads or tails. Quantum particles are like this, but infinitely more complex. An electron in an atom isn't at a specific point. It exists as a cloud of probability, simultaneously occupying all possible locations it could be, until a measurement forces it to choose one. It's not that we don't know where it is, it's that it isn't anywhere definite until measured. The reality of the electron, prior to observation, is intrinsically fuzzy and probabilistic. This fundamental uncertainty is formalized in Heisenberg's uncertainty principle. It states that there are certain pairs of properties of a particle that you cannot know with perfect precision simultaneously. The more precisely you know one, the less precisely you know one, the less precisely you can know the other. The most famous example is position and momentum. If you know an electron's exact position, you cannot know its exact momentum, its mass times its velocity, and vice versa. It's not a limitation of our instruments, it's a fundamental feature of reality itself. You can't observe a particle without disturbing it, and that disturbance impacts another property. It's like trying to accurately measure the temperature of a drop of water with a large hot thermometer. The thermometer itself changes the temperature you're trying to measure. The uncertainty isn't in our knowledge, but in the particle's very existence. Now let's turn our attention to another quantum phenomenon that truly beggars belief: quantum entanglement. This is perhaps the most mysterious and mind-boggling aspect of the quantum world, famously dubbed spooky action at a distance by Albert Einstein himself because he struggled to accept its implications. Imagine two quantum particles, say two electrons, that interact with each other in a specific way. Once they interact, they become entangled. This means that their fates are intertwined, no matter how far apart they are separated in space. If you measure a property of one entangled particle, say its spin, which is a quantum property analogous to a tiny magnetic orientation, the other entangled particle instantaneously takes on a correlated opposite spin. And this happens instantaneously, faster than the speed of light, regardless of whether the particles are inches apart or on opposite sides of the galaxy. Let's try to visualize this with an analogy. Imagine you have two perfectly balanced coins, one in London and one in New York. You flip the coin in London and it lands on heads. Instantly, the coin in New York, without any communication, without anyone even touching it, simultaneously flips to tails. And if the London coin landed on tails, the New York coin would instantly land on heads. The key here is instantaneously. There's no signal traveling between them. They are linked in a way that transcends classical notions of space and time. This violates our everyday understanding of causality, the idea that an event here can only affect an event there if some influence travels between them at a finite speed, or that objects only interact when they are physically close. Entanglement suggests a deeper, non-local connection woven into the very fabric of the universe. The implications of entanglement are staggering. If particles are truly entangled, it suggests that the information about their state isn't locally contained within each particle, but rather exists as a shared, holistic property of the entangled pair. When you measure one, you are not just discovering its state, you are forcing the entire entangled system to collapse into a definite state. It's as if two parts of a single, larger entity are distributed across space. This challenges the very notion of separate, independent objects. In some sense, everything that has ever interacted with anything else in the universe is to some degree entangled, though the effects become incredibly dilute and difficult to measure for macroscopic objects. At the quantum level, this interconnectedness is undeniable. Quantum mechanics, despite its strangeness, is not some obscure theoretical fringe science. It is one of the most successful scientific theories ever developed, underpinning much of our modern technology. The very microchips in your phone, the lasers in your DVD player, medical imaging technologies like MRI, and even the fundamental processes of chemistry and biology all rely on the principles of quantum mechanics. Without quantum mechanics, we simply couldn't explain how the sun shines or how atoms bond to form molecules. Its predictions have been verified with astonishing precision in countless experiments. This isn't just speculation, It's the fundamental reality at the smallest scales. The quantum world, therefore, forces us to confront a reality that is fundamentally probabilistic, uncertain, and interconnected. Particles don't have definite properties until they are measured. The act of observation is not passive. It actively influences what is observed. And distant particles can be intimately linked in a way that defies our conventional understanding of space and time. This is not the clockwork universe of Newton. It is a shimmering, probabilistic, interconnected realm where potentials are more real than actualities until observation solidifies them. This profound shift from a deterministic classical reality to a probabilistic quantum reality has led to intense philosophical debates among physicists themselves. Does a particle truly exist in a superposition of states before measurement, or is it merely our ignorance of its true state? Is reality fundamentally undetermined until an observer collapses the wave function? These are not settled questions, and different interpretations of quantum mechanics attempt to answer them in various ways, each with its own compelling yet equally strange implications. We will touch upon some of these interpretations, particularly the many worlds interpretation, in a later chapter, as it directly relates to the idea of parallel realities. For now, the key takeaway from this journey into the quantum realm is that the world we perceive with our everyday senses is a macroscopic average of billions upon billions of quantum events. The solidity of objects, the predictability of motion, the clear distinction between cause and effect, these are emergent properties that arise from the collective behavior of countless quantum particles. It's like seeing a clear image on a television screen. From a distance, it looks like a continuous picture, but if you get very close, you see individual pixels, discrete units of light. Quantum mechanics is the reality of those individual pixels, while classical physics describes the coherent image that emerges from them. So the next time you hold a seemingly solid object, remember that at its core, it's a shimmering cloud of probabilities, a dynamic dance of particles that don't have definite positions or properties until you interact with them. Your very presence, your act of observation, is an intimate part of this cosmic dance. The universe, at its most fundamental level, is not what it seems. It is a place of profound mystery, where the very act of looking helps to define what is real. This understanding lays the groundwork for the even grander scales of reality we will explore next, as we move from the infinitesimally small to the unimaginably vast, and discover how space and time themselves are not fixed backdrops, but dynamic players in the unfolding drama of the cosmos. Our journey into the nature of reality continues, with even more astonishing revelations ahead. Let's continue our expedition into the multifaceted nature of reality. Having ventured into the perplexing, probabilistic realm of the quantum, where particles defy classical logic and the very act of observation shapes what is perceived, we now shift our gaze from the infinitesimally small to the unimaginably vast. From the dance of subatomic particles, we ascend to the grand stage of the cosmos, to understand how space and time themselves are not merely passive backdrops for cosmic events, but active, dynamic participants in the unfolding drama of the universe. This chapter will delve into the revolutionary insights of Albert Einstein, revealing how the very fabric of our reality, the very dimensions we inhabit, can bend, warp, and even stretch, creating phenomena that were once considered the stuff of fantasy. For most of human history, and certainly throughout the reign of classical physics, space and time were considered absolute, unmoving, and independent entities. Space was thought of as a fixed, three-dimensional stage, an empty void where events unfolded. Time was a universal, relentless river, flowing uniformly and unchangingly for everyone, everywhere. A second was a second, regardless of your location or speed. These were the intuitive pillars of our perceived reality, deeply ingrained in our common sense. If two events happened simultaneously for one observer, they would happen simultaneously for all observers. This seemingly unassailable truth formed the bedrock of our understanding of the universe. However, at the beginning of the 20th century, a young, unassuming patent clerk named Albert Einstein shattered these deeply held beliefs with a series of groundbreaking theories that would forever alter our comprehension of reality. His insights, first with the theory of special relativity in 1905, and later with general relativity in 1915, revealed a universe far more interconnected, dynamic, and astonishing than anyone had previously imagined. The key to understanding this new reality lies in the concept of space-time. Imagine, if you can, that space and time are not separate entities, but rather interwoven into a single, four-dimensional fabric. Think of it like a giant, flexible trampoline. This isn't just a metaphor. It's how physicists visualize the universe at its most fundamental level. In this fabric, the three dimensions of space, up, down, left, right, forward, backward, are inextricably linked with the single dimension of time, past, future. Every event in the universe, from the fleeting existence of a quantum particle to the majestic sweep of a galaxy, occurs within this unified continuum of space-time. Let's begin with special relativity, which deals with how space and time are perceived by observers in uniform motion relative to one another. Einstein's brilliant insight started with two deceptively simple postulates. First, the laws of physics are the same for all observers in uniform motion. This means that if you're conducting an experiment on a train moving at a constant speed, the results should be identical to those conducted in a stationary laboratory, as long as the train isn't accelerating. Second, and this is the truly revolutionary part, the speed of light in a vacuum is the same for all observers, regardless of their own motion or the motion of the light source. This second postulate was a radical departure from classical physics. If you imagine throwing a ball from a moving car, its speed relative to the ground is the speed of the car plus the speed you threw the ball. But with light, this isn't the case. No matter how fast you are moving towards or away from a light source, you will always measure the speed of light to be approximately 299,702,458 meters per second. This fixed, cosmic speed limit has profound and counterintuitive consequences for our experience of space and time. If the speed of light is constant for everyone, something else has to give. And what gives are our traditional notions of absolute space and absolute time. Special relativity predicts phenomena that, to our everyday sensibilities, seem utterly impossible. Time dilation and length contraction. Imagine two observers. One, let's call her Alice, is stationary on Earth. The other, Bob, is traveling in a spaceship moving at an incredibly high speed, close to the speed of light. From Alice's perspective on Earth, Bob's clock on the spaceship will appear to run slower than her own clock. This isn't an optical illusion or a malfunction of Bob's clock. Time itself is genuinely passing more slowly for Bob relative to Alice. If Bob were to travel at 99.99% the speed of light for what felt like a year to him, upon returning to Earth, he would find that many decades had passed for Alice. His twin, who stayed on Earth, would be an old man, while Bob would have barely aged. This is the famous twin paradox, and it's not a paradox at all, but a verified consequence of relativity. Atomic clocks flown on airplanes, traveling at much slower but still significant speeds, consistently show minuscule but measurable time differences compared to stationary clocks on the ground. GPS satellites, moving rapidly in orbit, also experience time dilation, and their clocks must be precisely adjusted to account for relativistic effects. Otherwise, your GPS device would quickly become wildly inaccurate. Time, then, is not universal. Its passage is relative to the observer's motion. Furthermore, special relativity also predicts length contraction. From Alice's perspective, Bob's spaceship, as it zips past at near light speed, would appear to be shorter in the direction of its motion. The faster it moves, the more it contracts. Again, this isn't an illusion. The very fabric of space is compressed for objects moving at relativistic speeds. Imagine a spaceship designed to be 100 meters long. If it travels at extreme velocities, an observer on Earth might measure its length to be only 50 meters, or even less, depending on its speed. For Bob inside the spaceship, everything would feel normal, and he would measure his ship to be 100 meters long. But for Alice observing him, space itself is warped, and the dimensions of his ship are squished. These effects, time dilation and length contraction, are not separate phenomena, but two sides of the same coin. The consequences of an observer moving through the unified fabric of space-time. They highlight that simultaneity itself is relative. Two events that appear to happen at the exact same moment for Alice might occur at different times for Bob if he is moving relative to Alice. There is no universal now across the cosmos. This was a radical break from the classical notion of a synchronized universe. While special relativity dealt with uniform motion, Einstein soon realized that gravity, the force that binds us to Earth and governs the dance of planets and stars, could not be explained within this framework. He spent another decade grappling with this problem, culminating in his masterpiece, General Relativity. Here, the trampoline analogy for spacetime becomes even more powerful. Einstein proposed that gravity is not a mysterious force pulling objects together, but rather a manifestation of the curvature of spacetime. Imagine our flexible trampoline. If you place a bowling ball in the center of it, the fabric of the trampoline will sag and curve around the bowling ball. Now, if you roll a marble across the trampoline, it won't travel in a straight line. Instead, it will curve inwards towards the bowling ball, not because the bowling ball is pulling it, but because the marble is simply following the shortest possible path, or geodesic, within the curved fabric of the trampoline. In general relativity, massive objects like planets, stars, and galaxies literally warp and bend the fabric of spacetime around them, and what we perceive as gravity is simply the effect of other objects like light and other planets following these curves. This idea was breathtakingly revolutionary. The sun doesn't pull the Earth in its orbit. Instead, the sun's immense mass creates a deep well or depression in the spacetime fabric, and the Earth simply rolls along the curves of that well. The more massive an object, the greater the curvature it induces. This explained gravity not as a force, but as a geometric property of spacetime itself. The predictions of general relativity were equally astonishing and, over time, have been spectacularly confirmed by observation and experiment. One of the earliest confirmations came during a solar eclipse in 1919, when Arthur Eddington observed starlight bending around the sun. According to Newton, light shouldn't be affected by gravity, but according to Einstein, the sun's mass should curve spacetime, causing light passing near it to follow that curve, just as the marble followed the curve on the trampoline. Eddington's measurements precisely matched Einstein's predictions, catapulting Einstein into global fame. General relativity also predicts gravitational time dilation. Just as motion affects the passage of time, so too does gravity. Clocks run slower in stronger gravitational fields. For instance, a clock at the top of a skyscraper, being slightly further from Earth's gravitational pull, runs infinitesimally faster than a clock at the bottom. These differences are tiny, but again they are real and measurable. Comanche-Peer satellites, in addition to experiencing time dilation due to their speed, special relativity, also experience time dilation due to their slightly weaker gravitational environment, general relativity. Both effects must be accounted for to ensure precise navigation. This means that time is not only relative to motion, but also relative to the strength of gravity. There is no universal tempo to the cosmos. Time ebbs and flows, speeds up and slows down, depending on where you are in the universe's gravitational landscape. Perhaps the most extreme prediction of general relativity is the existence of black holes. If an object is incredibly massive and dense, it can warp spacetime so profoundly that it creates a region where the curvature is so extreme that nothing, not even light, can escape its gravitational pull. Imagine our trampoline analogy, but instead of just a depression, the bowling ball creates an infinitely deep well, a bottomless pit from which nothing can emerge. This boundary, beyond which escape is impossible, is called the event horizon. Once something crosses the event horizon, it is irrevocably lost to our universe. The spacetime inside a black hole is so distorted that all paths lead inward, to a point of infinite density called a singularity, where our current laws of physics break down. Black holes, once purely theoretical curiosities, are now observed astrophysical phenomena, with supermassive black holes residing at the centers of most galaxies, including our own Milky Way. Their existence is a powerful testament to the bizarre dynamic nature of spacetime. Another fascinating consequence of general relativity is the idea of gravitational waves. Just as accelerating electrical charges produce ripples in the electromagnetic field, light waves, Einstein predicted that accelerating massive objects, like two black holes spiraling into each other, or two neutron stars colliding, should produce ripples in the fabric of spacetime itself. These ripples, or gravitational waves, would travel at the speed of light, carrying energy away from their source. For decades, these waves were elusive, their effects too subtle to detect. But in 2015, the LIGO, Laser Interferometer Gravitational Wave Observatory, this groundbreaking observation not only confirmed another key prediction of general relativity, but also opened a new window onto the universe, allowing us to hear cosmic cataclysms rather than just see them with light. It was a profound confirmation that space-time is not static, but a dynamic, undulating medium. The implications of space-time curvature extend far beyond the immediate vicinity of massive objects. General relativity is also the framework within which we understand the universe on its largest scales, the cosmological scale. It's the foundation of the Big Bang Theory, our prevailing scientific model for the origin and evolution of the universe. The theory doesn't describe an explosion in space, but rather an expansion of space itself. Imagine inflating a balloon with dots on its surface. As the balloon inflates, the dots move further apart, not because they are moving across the surface, but because the surface itself is expanding. Similarly, galaxies are not rushing away from a central point of explosion. The space between galaxies is expanding, stretching the fabric of spacetime. This expansion causes the light from distant galaxies to stretch, making it appear redder, a phenomenon known as cosmological redshift, which is precisely what we observe. This cosmic expansion means that the universe we inhabit is not static. It's an evolving entity, with its geometry and destiny intimately tied to the amount of matter and energy within it. The amount of matter and energy determines the overall curvature of the universe, whether it is flat, like a tabletop, open, like a saddle. Our current observations suggest that the universe is remarkably flat, implying a delicate balance of energy and matter. This flatness is one of the profound mysteries of cosmology, as it requires a very specific initial condition for the universe, leading some theories to suggest concepts like cosmic inflation, a brief period of extremely rapid expansion in the very early universe. So, from the quantum dance of uncertainty to the grand cosmic ballet of spacetime, we see that reality is a dynamic, fluid, and interconnected tapestry. The solid, unchanging reality of our everyday lives is but an emergent property, a convenient approximation that masks deeper, more profound truths. Time is not universal. It stretches and contracts. Space is not flat. It bends and warps. Gravity is not a force. It is the geometry of the universe itself. These insights from special and general relativity don't just offer abstract mathematical descriptions. They provide a profound new way of seeing the cosmos, one where the very stage of existence is a character in its own right. The implications of this dynamic space-time are enormous. It affects how we communicate across vast distances, how we navigate our planet, and how we search for answers to the most fundamental questions about cosmic origins and ultimate destiny. It lays the groundwork for understanding the structure of galaxies, the formation of stars, and the very possibilities of space travel, even hinting at exotic phenomena like wormholes, theoretical tunnels through space-time that could potentially connect distant regions of the universe or even different times. While these remain highly speculative, they emerge directly from the equations of general relativity, showcasing the astonishing possibilities inherent in a flexible, warpable space-time. As we move forward, holding on to this new understanding of a relative, curved and expanding space-time will be crucial, because if space and time are not fixed, and if the universe itself is a dynamic entity, what then are the implications for its scale? How vast is it truly? And could there be more than one? Our next chapter will take this understanding of a vast and expanding universe and push it to its ultimate limit, exploring the mind-boggling possibility that our entire universe might be just one of an infinite number, floating within a grander cosmic ocean. The journey into the multiverse awaits, and the foundations of space-time we've just explored are essential to comprehending its potential realities. Our journey has revealed that the universe is far stranger at its smallest and largest scales than our everyday senses suggest. Now we expand our perspective even further, to the grandest canvas of all, the universe itself. In this chapter, we will confront the unimaginable vastness of the cosmos, discuss what we can actually observe, and then push beyond that horizon to consider what might lie in the realms forever hidden from our direct view, laying the groundwork for the most audacious hypothesis of all, the multiverse. This realization began with the meticulous observations of astronomers like Edwin Hubble in the late 1920s. Using powerful telescopes, Hubble observed that distant galaxies were not just moving away from us, but the further away they were, the faster they appeared to be receding. This phenomenon, known as Hubble's law, is the observational cornerstone of the expanding universe. The light from these receding galaxies was also found to be red-shifted, meaning its wavelengths were stretched towards the red end of the spectrum, similar to how the pitch of an ambulance siren drops as it moves away from you. This cosmological redshift is not due to galaxies moving through space, but rather due to the expansion of space itself, stretching the light waves as they travel across vast cosmic distances. It's a direct observational signature of an expanding universe. Our exploration thus far has revealed that the universe is not a static, unchanging entity. It is a dynamic, evolving tapestry, woven from the interactions of quantum particles and shaped by the curvature of spacetime. One of the most profound discoveries of the 20th century, firmly rooted in Einstein's general theory of relativity, is that our universe is not only vast, but it is also expanding. Imagine, once again, the surface of a balloon being inflated. If you drew dots on that balloon, representing galaxies, as the balloon expands, all the dots move away from each other. Crucially, no single dot is at the center of the expansion. Every dot sees every other dot moving away from it. This is a crucial analogy for understanding the expansion of our universe. Galaxies are not rushing away from a central point in space. Rather, the space between galaxies is stretching, causing them to recede from one another. This expansion has a profound implication. If the universe is expanding today, then in the past it must have been smaller and denser. Tracing this expansion backward in time, all the way to its theoretical beginning, leads us to the concept of the Big Bang. It's vital to clarify what the Big Bang is and isn't. It wasn't an explosion in space, but rather the rapid expansion of space from an unimaginably hot, dense state. It wasn't a point in space, but a state of the universe where all of space, time, and matter, as we know it, originated and began its expansion. The Big Bang theory describes the evolution of the universe from that initial hot, dense state, not necessarily the creation of that state. Our current understanding allows us to trace the universe back to about 13.8 billion years ago, which is the estimated age of the universe. Further compelling evidence for the Big Bang came in 1964 with the accidental discovery of the cosmic microwave background, CMB, radiation. Imagine the universe, just a few 100,000 years after the Big Bang, as an incredibly hot, dense plasma, too hot for electrons to bind with atomic nuclei. Light particles, photons, were constantly scattering off these free electrons, unable to travel far. It was like being in a dense fog. As the universe expanded, it cooled. Eventually, when the temperature dropped to about 3,000 degrees Celsius, electrons could combine with nuclei to form neutral atoms. At this point, the universe became transparent, and the photons were finally free to stream across space. These photons, released at that ancient moment, have been traveling and cooling ever since. Today, due to the continuous expansion of space stretching their wavelengths, they are observed as faint microwave radiation coming from every direction in the sky, a ghostly echo of the universe's fiery birth. The CMB is considered the most compelling evidence for the Big Bang, a snapshot of the universe when it was just a cosmic infant. Its incredibly uniform temperature across the sky, with tiny fluctuations that seeded the formation of galaxies, provides a powerful confirmation of our cosmological model. The observable universe, then, is a sphere centered on us, defined by how far light has had time to travel since the Big Bang. Because light has a finite speed, and the universe has a finite age, there's a limit to how far back in time, and thus how far in space we can see. This horizon, the cosmological horizon, represents the edge of our observable universe. Currently, This horizon is estimated to be about 46.5 billion light-years away in every direction. Note that this is larger than 13.8 billion light-years, the age of the universe, because the universe has been expanding during the time light has been traveling towards us. It's like looking at a distant ship on the ocean. You're seeing it where it was when the light left it, but the ship has since moved further away. Our observable universe is a sphere with us at its center, encompassing all the light and information that has reached us over cosmic history. This means that there are vast regions of the universe, teeming with galaxies, stars and planets, that we will never be able to see because the light from them has not yet had enough time to reach us, or because the expansion of space is carrying them away from us faster than their light can travel. This unobservable universe is, in essence, another reality, one that exists, is physical, and is subject to the same laws of physics as our own, but which is forever beyond our direct empirical grasp. It's like being on a ship in the middle of a vast ocean. You can only see to the horizon, but you know logically that the ocean continues far beyond your sight. Think about it this way. The expansion we observe, driven by the Big Bang, isn't unique to our location. Every point in space is experiencing the same expansion. This is tied to a concept known as the cosmological principle, which posits that on large scales, the universe is homogeneous and isotropic. Homogeneous means it's roughly the same everywhere. Galaxies are distributed evenly. There are no special centers or edges. Isotropic means it looks the same in every direction. If this principle holds true, and all our observations support it on scales larger than galaxy clusters, then there's no reason to assume that the expansion abruptly stops at our observable horizon. It continues, extending indefinitely. But here's the crucial question. Does the universe end at this observable horizon? Or is there more to the universe beyond what we can possibly see? The prevailing scientific consensus, based on our current understanding of physics and observations, strongly suggests that the universe extends far, far beyond our observable horizon. In fact, it is highly probable that the universe is either infinitely large. So if the universe is so much larger than what we can see, what might be out there? The possibilities are staggering. If the universe is truly infinite, or at least astronomically large, then by the laws of probability, anything that can happen will happen, given enough space. This leads to fascinating, almost unsettling conclusions. Consider the arrangement of particles in any given volume of space. There's a finite number of ways that particles can arrange themselves within a given volume, even if that number is incredibly vast. If the universe is truly infinite, or if it's a flat universe that goes on forever, then eventually, far beyond our cosmic horizon, there must be other patches of space where the arrangement of particles is identical to ours. This is the simplest and perhaps most widely accepted form of the multiverse hypothesis, often called the level 1 multiverse. In a truly infinite universe, not only would there be exact copies of you reading this exact sentence, but also variations, worlds where you made slightly different choices, or where fundamental constants were slightly different. These are not necessarily separate universes in a dramatic parallel dimension sense, but rather distinct regions within the same vast, possibly infinite, overarching universe, too far away for any interaction or observation. It's like having an infinite deck of cards. Eventually, every possible hand, every possible shuffle will repeat. If the universe is infinitely large, then given enough cosmic real estate, everything you can imagine and everything you can't will exist, perhaps many times over. This level of the multiverse simply states that space is so vast that repetitions are inevitable. Now, some theories of inflation, particularly eternal inflation, suggest that this inflationary process, once it starts, never completely stops everywhere. Instead, it continues indefinitely in some regions, while in other regions it bubbles off, ending the inflation locally and giving rise to new, expanding bubble universes. Our own universe in this scenario would be just one such bubble, and within this grand, eternally inflating multiverse, different bubble universes could have different fundamental constants, different laws of physics, or different numbers of dimensions. Imagine an infinite ocean of inflating spacetime, constantly spawning new bubbles, each a self-contained universe with its own unique set of rules. One proposed solution to the fine-tuning problem leads to a more complex form of the multiverse, often called the Level 2 multiverse, or the theory of bubble universes. This concept arises from a theoretical extension of the Big Bang model called cosmic inflation. Inflation posits that in the very first tiny fraction of a second after the Big Bang, the universe underwent an incredibly rapid exponential expansion, far faster than its current expansion rate. This inflationary period solves several problems with the standard Big Bang model, such as why the universe is so uniformly smooth on large scales, and why it appears so geometrically flat. But the unobservable universe isn't just about repetition, it's also about what kind of universe we live in. We exist in a universe with specific physical laws, specific fundamental constants, the speed of light, the strength of gravity, the mass of an electron, and so on. These constants are incredibly finely tuned for the existence of life. If they were even slightly different, galaxies wouldn't form, stars wouldn't ignite, and atoms as we know them wouldn't exist, let alone life. This observation is often referred to as the fine-tuning problem. Why are these constants precisely right for us? Is it just a lucky coincidence, or is there something more to it? Our journey has revealed that the universe is far stranger at its smallest and largest scales than our everyday senses suggest. Now we expand our perspective even further, to the grandest canvas of all, the universe itself. In this chapter, we will confront the unimaginable vastness of the cosmos, discuss what we can actually observe, and then push beyond that horizon to consider what might lie in the realms forever hidden from our direct view, laying the groundwork for the most audacious hypothesis of all, the multiverse. Our exploration thus far has revealed that the universe is not a static, unchanging entity. It is a dynamic, evolving tapestry, woven from the interactions of quantum particles and shaped by the curvature of spacetime. One of the most profound discoveries of the 20th century, firmly rooted in Einstein's general theory of relativity, is that our universe is not only vast, but it is also expanding. Imagine, once again, the surface of a balloon being inflated. If you drew dots on that balloon, representing galaxies, as the balloon expands, all the dots move away from each other. Crucially, no single dot is at the center of the expansion. Every dot sees every other dot moving away from it. This is a crucial analogy for understanding the expansion of our universe. Galaxies are not rushing away from a central point in space. Rather, the space between galaxies is stretching, causing them to recede from one another. This realization began with the meticulous observations of astronomers like Edwin Hubble in the late 1920s. Using powerful telescopes, Hubble observed that distant galaxies were not just moving away from us, but the further away they were, the faster they appeared to be receding. This phenomenon, known as Hubble's law, is the observational cornerstone of the expanding universe. The light from these receding galaxies was also found to be red-shifted, meaning its wavelengths were stretched towards the red end of the spectrum, similar to how the pitch of an ambulance siren drops as it moves away from you. This cosmological redshift is not due to galaxies moving through space, but rather due to the expansion of space itself, stretching the light waves as they travel across vast cosmic distances. It's a direct observational signature of an expanding universe. This expansion has a profound implication. If the universe is expanding today, then in the past it must have been smaller and denser. Tracing this expansion backward in time, all the way to its theoretical beginning, leads us to the concept of the Big Bang. It's vital to clarify what the Big Bang is and isn't. It wasn't an explosion in space, but rather the rapid expansion of space from an unimaginably hot, dense state. It wasn't a point in space, but a state of the universe where all of space, time, and matter, as we know it, originated and began its expansion. The Big Bang theory describes the evolution of the universe from that initial hot, dense state, not necessarily the creation of that state. Our current understanding allows us to trace the universe back to about 13.8 billion years ago, which is the estimated age of the universe. Further compelling evidence for the Big Bang came in 1964 with the accidental discovery of the cosmic microwave background, CMB, radiation. Imagine the universe, just a few 100,000 years after the Big Bang, as an incredibly hot, dense plasma too hot for electrons to bind with atomic nuclei. Light particles, photons, were constantly scattering off these free electrons, unable to travel far. It was like being in a dense fog. As the universe expanded, it cooled. Eventually, when the temperature dropped to about 3000 degrees Celsius, electrons could combine with nuclei to form neutral atoms. At this point, the universe became transparent, and the photons were finally free to stream across space. These photons, released at that ancient moment, have been traveling and cooling ever since. Today, due to the continuous expansion of space stretching their wavelengths, they are observed as faint microwave radiation coming from every direction in the sky, a ghostly echo of the universe's fiery birth. The CMB is considered the most compelling evidence for the Big Bang, a snapshot of the universe when it was just a cosmic infant. Its incredibly uniform temperature across the sky, with tiny fluctuations that seeded the formation of galaxies, provides a powerful confirmation of our cosmological model. The observable universe, then, is a sphere centered on us, defined by how far light has had time to travel since the Big Bang. Because light has a finite speed, and the universe has a finite age, there's a limit to how far back in time, and thus how far in space we can see. This horizon, the cosmological horizon, represents the edge of our observable universe. Currently, this horizon is estimated to be about 46.5 billion light-years away in every direction. Note that this is larger than 13.8 billion light-years, the age of the universe, because the universe has been expanding during the time light has been traveling towards us. It's like looking at a distant ship on the ocean. You're seeing it where it was when the light left it, but the ship has since moved further away. Our observable universe is a sphere with us at its center, encompassing all the light and information that has reached us over cosmic history. But here's the crucial question. Does the universe end at this observable horizon? Or is there more to the universe beyond what we can possibly see? The prevailing scientific consensus, based on our current understanding of physics and observations, strongly suggests that the universe extends far, far beyond our observable horizon. In fact, it is highly probable that the universe is either infinitely large. Think about it this way. The expansion we observe, driven by the Big Bang, isn't unique to our location. Every point in space is experiencing the same expansion. This is tied to a concept known as the cosmological principle, which posits that on large scales, the universe is homogeneous and isotropic. Homogeneous means it's roughly the same everywhere. Galaxies are distributed evenly. There are no special centers or edges. Isotropic means it looks the same in every direction. If this principle holds true, and all our observations support it on scales larger than galaxy clusters, then there's no reason to assume that the expansion abruptly stops at our observable horizon. It continues, extending indefinitely. This means that there are vast regions of the universe, teeming with galaxies, stars and planets, that we will never be able to see, because the light from them has not yet had enough time to reach us, or because the expansion of space is carrying them away from us faster than their light can travel. This unobservable universe is, in essence, another reality, one that exists, is physical, and is subject to the same laws of physics as our own, but which is forever beyond our direct empirical grasp. It's like being on a ship in the middle of a vast ocean. You can only see to the horizon, but you know logically that the ocean continues far beyond your sight. So if the universe is so much larger than what we can see, what might be out there? The possibilities are staggering. If the universe is truly infinite, or at least astronomically large, then by the laws of probability, anything that can happen will happen, given enough space. This leads to fascinating, almost unsettling conclusions. Consider the arrangement of particles in any given volume of space. There's a finite number of ways that particles can arrange themselves within a given volume, even if that number is incredibly vast. If the universe is truly infinite, or if it's a flat universe that goes on forever, then eventually, far beyond our cosmic horizon, there must be other patches of space where the arrangement of particles is identical to ours. This is the simplest and perhaps most widely accepted form of the multiverse hypothesis, often called the level 1 multiverse. In a truly infinite universe, not only would there be exact copies of you reading this exact sentence, but also variations, worlds where you made slightly different choices, or where fundamental constants were slightly different. These are not necessarily separate universes in a dramatic parallel dimension sense, but rather distinct regions within the same vast, possibly infinite, overarching universe, too far away for any interaction or observation. It's like having an infinite deck of cards. Eventually, every possible hand, every possible shuffle will repeat. If the universe is infinitely large, then given enough cosmic real estate, everything you can imagine and everything you can't will exist, perhaps many times over. This level of the multiverse simply states that space is so vast that repetitions are inevitable. But the unobservable universe isn't just about repetition, it's also about what kind of universe we live in. We exist in a universe with specific physical laws, specific fundamental constants, the speed of light, the strength of gravity, the mass of an electron, and so on. These constants are incredibly finely tuned for the existence of life. If they were even slightly different, galaxies wouldn't form, stars wouldn't ignite, and atoms as we know them wouldn't exist, let alone life. This observation is often referred to as the fine-tuning problem. Why are these constants precisely right for us? Is it just a lucky coincidence, or is there something more to it? One proposed solution to the fine-tuning problem leads to a more complex form of the multiverse, often called the Level 2 multiverse, or the theory of bubble universes. This concept arises from a theoretical extension of the Big Bang model called cosmic inflation. Inflation posits that in the very first tiny fraction of a second after the Big Bang, the universe underwent an incredibly rapid exponential expansion, far faster than its current expansion rate. This inflationary period solves several problems with the standard Big Bang model, such as why the universe is so uniformly smooth on large scales, and why it appears so geometrically flat. Now, some theories of inflation, particularly eternal inflation, suggest that this inflationary process, once it starts, never completely stops everywhere. Instead, it continues indefinitely in some regions, while in other regions it bubbles off, ending the inflation locally and giving rise to new, expanding bubble universes. Our own universe in this scenario would be just one such bubble, and within this grand, eternally inflating multiverse, different bubble universes could have different fundamental constants, different laws of physics, or different numbers of dimensions. Imagine an infinite ocean of inflating spacetime, constantly spawning new bubbles, each a self-contained universe with its own unique set of rules. This would explain the fine-tuning. We exist in this universe because its constants happen to be conducive to our existence. If there are countless other universes with different parameters, then it's not surprising that at least one of them would have the specific conditions necessary for life to arise. It's like a cosmic lottery. If enough tickets are bought, someone is bound to win. We happen to be in the universe that won the life lottery. This idea is powerful because it takes something that seems like an improbable coincidence and transforms it into a statistical inevitability within a larger framework. Each bubble universe, including our own, would be an isolated pocket, expanding within the larger inflating multiverse, completely causally disconnected from the others, meaning we could never observe them directly. The concept of the unobservable universe, whether as simply an incredibly vast extension of our own universe, or as a collection of disconnected bubble universes, fundamentally changes our perspective. It moves us from viewing our universe as the totality of existence to seeing it as potentially just one small, perhaps even insignificant, part of a much grander cosmic whole. This challenges our anthropocentric view of the cosmos, suggesting that our particular reality, with its specific laws and conditions, is merely one outcome among an infinite spectrum of possibilities. Furthermore, the unobservable universe brings with it questions about the limits of our knowledge. Can we ever truly know the extent of reality if so much of it is forever beyond our reach? While we cannot directly observe these distant or separate universes, their existence is a logical extension of our best current scientific theories, supported by mathematical models and philosophical arguments based on probability. The pursuit of scientific knowledge is about building models that best explain our observations and make testable predictions. The multiverse, in its various forms, arises as a compelling answer to some of the deepest questions about our universe's properties. Our understanding of the universe's ultimate scale is still evolving. We constantly refine our measurements of its expansion rate, its age, and its composition. We search for subtle clues in the cosmic microwave background radiation that might hint at inflationary processes or the presence of other universes. We push the boundaries of particle physics to understand the fundamental forces that govern the universe at its birth, hoping to find theoretical connections to these larger cosmic structures. The journey into the unobservable universe is a powerful reminder of the humility required in scientific inquiry. Just as we once believed Earth was the center of the cosmos, and then our solar system, and then our galaxy, we are now confronted with the possibility that our entire universe is but a speck in a cosmic ocean. This expansive view compels us to consider the limits of our perception and the profound implications of a reality that stretches far beyond what our most powerful telescopes can ever hope to capture. It sets the stage for even more radical ideas about reality, including the possibility that our very reality is intertwined with every possible choice, or that it is not physical at all, but rather a simulation. But before we tackle those profound concepts, understanding the sheer scale and potential multiplicity suggested by the unobservable universe is a crucial next step in comprehending the true meaning of reality. The very idea of cosmic repetition, of countless other cosmic realms, opens the door to even more perplexing questions about our place in the grand scheme of things. Our exploration of reality has so far led us down pathways less traveled by our everyday senses. From the probabilistic weirdness of the quantum realm, where particles exist in states of superposition and are mysteriously entangled across vast distances, to the grand cosmic stage of spacetime, a dynamic fabric that bends, warps, and expands, giving rise to gravity and the very evolution of our observable universe. We concluded our last discussion by venturing beyond our cosmic horizon, contemplating the sheer, incomprehensible scale of the universe that lies beyond our immediate perception, and introducing the tantalizing idea that this immense expanse might inherently lead to repetitions of ourselves and our world, simply due to the vastness of available cosmic real estate. Now we take the next logical, and perhaps most mind-boggling leap, the audacious hypothesis of the multiverse. This is not science fiction. It is a serious and active area of theoretical physics, born from the logical extensions of our most successful scientific theories. The concept of the multiverse is not a single unified idea, but rather a collection of distinct, yet often interconnected, scientific hypotheses, each arising from different branches of physics and cosmology. They all share a common thread: the idea that our universe, the one we inhabit and observe, is not the only universe. Instead, it is merely one in a potentially infinite ensemble of other universes, each with its own existence, and sometimes its own unique set of physical laws and conditions. This is a profound shift in perspective, moving from a single, isolated cosmic entity to an almost unimaginably vast cosmic ecosystem. Let's revisit the simplest form, the Level 1 multiverse, which we touched upon at the end of our last chapter. This concept stems directly from the idea of an infinite, or at least astronomically large universe. If the universe truly extends indefinitely beyond our observable horizon, and if matter and energy are distributed roughly evenly throughout this infinite expanse, as suggested by the cosmological principle, then the laws of probability dictate that repetitions are inevitable. Imagine shuffling a deck of cards. There's a finite number of ways to arrange those cards. If you shuffle it enough times, eventually you'll repeat previous arrangements. The universe in this analogy is a vastly larger but still finite collection of particles within any given cosmic volume. The number of ways these particles can arrange themselves is immense, but finite. If you have an infinite amount of space, then any given arrangement of particles, including the precise arrangement that constitutes our Earth, our solar system, our galaxy, and indeed every atom in your body, must eventually repeat, not just once, but an infinite number of times. This means that billions of light years away, far beyond the reach of any telescope or any future space probe, there could be an exact copy of you, living your exact life, reading this exact sentence, and another copy, where you made a slightly different choice moments ago, leading to a diverging future, and another where everything is the same, but the coffee mug on your table is a different color. These aren't parallel dimensions in a mystical sense, but rather distinct, causally disconnected regions within the same overarching, infinitely expanding universe. They are separated by such immense distances that no light or information could ever travel between them within the age of the universe. While scientifically plausible, this level 1 multiverse offers a strange kind of comfort, or perhaps a chilling existential dread, depending on your perspective. Every possibility, every variation of your life is playing out somewhere, always. It emphasizes the incredible vastness of what already is, even if we cannot perceive it directly. Moving beyond simple cosmic repetition, we encounter the level 2 multiverse, which stems from the powerful and well-supported theory of cosmic inflation, particularly the idea of eternal inflation. As we discussed, inflation proposes a period of extremely rapid, exponential expansion in the universe's infancy, solving several cosmic puzzles. But what if inflation, once it begins, never truly stops everywhere? Imagine a giant frothing ocean of spacetime, constantly expanding and creating new regions. In some of these regions, the inflationary expansion might slow down and cease, much like boiling water eventually cools. When this happens, a bubble of non-inflating spacetime forms, and within this bubble, the conditions for a Big Bang, as we understand it for our own universe, can arise. Our universe in this scenario is one such bubble. The key insight of eternal inflation is that the overall inflationary process continues indefinitely, churning out an infinite number of such bubble universes. Each bubble universe is like a separate pocket, expanding independently within the larger, inflating megaverse. And here's where it gets truly mind-bending. The fundamental physical constants, the very laws of physics that govern each bubble, could be different. This is because the precise way inflation ends within a given bubble, and the specific quantum fluctuations that occur during its formation, could lead to different vacuum states, which in turn manifest as different strengths of forces, different masses for particles, and even different numbers of spatial dimensions within each universe. This level 2 multiverse offers a compelling solution to the fine-tuning problem that we touched upon earlier. Our universe possesses a seemingly improbable set of physical constants that are precisely calibrated for the existence of stars, galaxies, and life as we know it. For instance, if the strong nuclear force were slightly weaker, atomic nuclei wouldn't hold together. If it were slightly stronger, stars would burn out too quickly. If the cosmological constant, which drives the universe's accelerating expansion, were just a tiny bit larger, the universe would have expanded too rapidly for galaxies to form. The probability of these constants arising purely by chance in a single universe seems incredibly small. But if there are an infinite number of bubble universes, each with potentially different laws and constants, then it becomes statistically inevitable that at least one of them would have the just right conditions for conscious observers to emerge. We find ourselves in this universe precisely because it's one of the rare ones where life is possible. The level 2 multiverse transforms the question of why us into, of course, us. Someone has to be in the life-friendly universes. These bubble universes are causally disconnected because of the ongoing inflation between them. The space separating these bubbles expands so rapidly that light or any other form of information could never travel from one bubble to another. They are effectively separate realities, coexisting within a larger, unobservable cosmic landscape, yet entirely isolated from one another. This means we could never directly observe or interact with these other bubble universes, making their existence a subject of theoretical deduction rather than direct empirical verification. However, the theoretical framework that leads to their prediction, eternal inflation, is robustly supported by evidence from the cosmic microwave background and other cosmological observations, giving the level 2 multiverse considerable scientific weight. Beyond the vast spatial repetitions and the bubbling cosmic foam lies the level 3 multiverse, which emerges directly from the quantum weirdness we explored in Chapter 2. Specifically from the many worlds interpretation, MWI, of quantum mechanics. Recall the double-slit experiment, where a particle like an electron seems to exist in a superposition of states, passing through both slits simultaneously until it is observed, at which point it collapses into a definite state, taking a single path. The MWI offers a radical solution to this perplexing collapse problem. Instead of the wave function actually collapsing, the MWI proposes that every time a quantum measurement or interaction occurs, the universe splits into multiple parallel universes. In this interpretation, every possible outcome of a quantum event is realized in its own separate universe. So in the double-slit experiment, when the electron chooses to go through the left slit in our universe, there's another parallel universe where it chose the right slit. When you make a decision, say, whether to have coffee or tea, in one universe you choose coffee, and in another, equally real universe, a version of you chooses tea. And these universes continue to split with every subsequent quantum interaction, at every moment, for every particle, for every conscious being. The number of parallel universes generated by the MWI is truly astronomical, perhaps even infinite, growing exponentially with every quantum choice. It's crucial to understand that these aren't just hypothetical possibilities. In the MWI, they are all equally real, equally existing branches of reality. There isn't a single future, there are countless futures, all playing out simultaneously in different branches of the quantum multiverse. The you reading this now is just one of an infinite number of your counterparts, each experiencing a slightly different branch of reality. This means that every quantum uncertainty, every roll of the dice in the subatomic world, leads to a branching of reality. The collapse of the wave function, then, isn't a physical event. It's simply the subjective experience of an observer being located within one specific branch of an ever-branching reality. The macroscopic world we experience, with its apparent certainty, is an emergent property of our inability to perceive the other branches. We are confined to our own particular path, oblivious to the countless others branching off in parallel. The MWI is controversial among physicists, not because it's scientifically disproven, it's consistent with all quantum experiments, but because of its profound philosophical implications and the sheer number of parallel realities it postulates. How could we ever verify such a thing? Proponents argue that it's the simplest interpretation, avoiding the need for an arbitrary collapse mechanism. Critics find it extravagant, arguing for more parsimonious explanations. Nevertheless, it is a powerful and elegant solution to the quantum measurement problem, offering a coherent picture of how quantum probabilities translate into definite outcomes in our perceived reality. If the MWI is correct, then our existence is not just one possibility in a vast cosmic landscape, but one actualization among an infinite ensemble of actualizations, all simultaneously unfolding. Finally, we encounter the level 4 multiverse, the most abstract and speculative, yet potentially the most encompassing. This hypothesis, often put forth by cosmologist Max Tegmark, suggests that every mathematically consistent physical structure exists as a separate universe. If a universe can be described by a set of mathematical equations, then it exists. This goes beyond different initial conditions or different physical constants. It encompasses universes where the very fundamental laws of physics are different. Imagine a universe where gravity is an inverse cube law, or where space-time has 5 dimensions, or where there are entirely different types of particles and forces. If such a universe is mathematically coherent and self-consistent, then according to this hypothesis, it exists. The level 4 multiverse essentially equates existence with mathematical existence. If a mathematical structure is conceivable, it's real. This is a very deep and philosophical concept, implying that the universe is not just described by mathematics, but is mathematics. Our physical reality, with its specific laws and constants, would simply be one of these existing mathematical structures. This hypothesis implies an infinite hierarchy of multiverses, encompassing all possible mathematical frameworks that could define a universe. It's the ultimate answer to why these laws, because all possible laws exist. This is, of course, the most challenging form of the multiverse to grasp and verify, pushing the boundaries of what we traditionally consider science, blurring the lines between physics, mathematics, and philosophy. It suggests that any universe you can coherently describe, no matter how alien, has a real existence. The scientific community holds varying degrees of acceptance for these different levels of the multiverse. The level 1 multiverse is widely considered a logical consequence if the universe is infinite. The level 2 multiverse, stemming from eternal inflation, is strongly supported by inflationary theory, which itself has significant observational backing. The level 3 multiverse, the many worlds interpretation, is a valid and self-consistent interpretation of quantum mechanics, though its philosophical implications are intensely debated. The level 4 multiverse remains highly speculative, a frontier of theoretical physics and philosophy. Why does the concept of a multiverse matter? Beyond its profound philosophical implications for our place in existence, it offers potential solutions to some of the deepest mysteries in physics. It can explain the fine-tuning of our universe, suggesting it's not a cosmic fluke, but a statistical inevitability within a larger ensemble. It can provide a framework for unifying seemingly disparate theories, or for understanding why our universe has the specific laws and constants it does. It shifts the question from why this universe to why are we observing this universe, with the answer often pointing to the anthropic principle, which states that the universe must be compatible with the existence of conscious observers. The search for empirical evidence for a multiverse, while challenging, is ongoing. Scientists look for subtle imprints in the cosmic microwave background radiation that might suggest collisions with other bubble universes. They explore the predictions of string theory and other theories of quantum gravity that naturally lead to multiverse scenarios. They delve deeper into the mathematical structures that could describe fundamental reality, searching for connections that transcend our single universe. While direct observation remains elusive, the indirect clues, the theoretical consistency, and the explanatory power of the multiverse hypothesis make it a compelling subject of modern scientific inquiry. The very idea of a multiverse reshapes our cosmic address. We are no longer simply residents of Earth or the Milky Way, or even this universe. We might be inhabitants of a single bubble within an infinite foam, or a single branch within an ever-splitting quantum tree, or a single mathematical structure within an infinite library of possibilities. This expansive view of reality forces us to confront the limits of our perception and challenges our innate human tendency to assume that what we see is all there is. It encourages a profound humility and an exhilarating sense of wonder about the true scale and complexity of existence. As we move forward, holding on to the understanding of a potentially infinite collection of universes will be crucial, because if reality can be so vast, so varied, and so multi-branched, what does that mean for our own sense of self, our consciousness, and our perception? If our universe is just one among many, could our very existence be part of a larger, unseen fabric? This leads us to consider the idea of hidden dimensions, layers of reality beyond our three spatial dimensions, which could provide pathways between these universes or even constitute entire other realities within our own. The next chapter will explore these higher dimensions, another frontier of reality that defies our everyday intuition. We've grappled with particles that exist everywhere at once, and universes that might be endlessly branching or bubbling into existence. Now we delve deeper into the most bewildering aspect of quantum mechanics, one that directly challenges our sense of individual existence and hints at profound, unseen connections across what we perceive as distinct realities. The phenomenon of quantum entanglement, and its most radical interpretation, the many worlds interpretation of parallel universes. Recall from our discussion in Chapter 2 that quantum entanglement was dubbed spooky action at a distance by Albert Einstein. This is the phenomenon where two or more quantum particles become intrinsically linked, so that the measurement of a property of one instantaneously determines the corresponding property of the others, no matter how far apart they are. Imagine for a moment two coins that are magically linked. You prepare them in a special way, then give one to a friend who flies to the other side of the galaxy. You flip your coin and it lands on heads. Instantly, the coin in your friend's hand, without any communication, without any signal traveling between them, simultaneously lands on tails. And if yours landed on tails, theirs would land on heads. The key is that before you flipped your coin, neither coin was definitely heads or tails. They were in a superposition, a probabilistic blend of both. It was only upon your measurement that both instantly assumed definite correlated states. This defies our classical understanding of locality, the idea that objects can only influence each other if they are physically close, or if an influence travels between them at a finite speed. Entanglement suggests a deeper, non-local connection, an intrinsic shared identity, even when separated by light years. This spooky action is not merely a theoretical curiosity. It has been rigorously proven in countless experiments, even over vast distances, forming the bedrock of emerging technologies like quantum computing and quantum cryptography. But what does it truly mean? How can information about one particle instantaneously influence another without violating the cosmic speed limit of light? This is where interpretations of quantum mechanics diverge, and where the concept of parallel realities finds a compelling, albeit radical, home. For decades, the most common way to think about this was the idea of wave function collapse. According to this interpretation, quantum particles exist as wave functions, mathematical descriptions of all their possible states and the probabilities of finding them in those states. When we perform a measurement, this wave function collapses and the particle chooses one definite state from its many possibilities. But what causes this collapse? Is it the act of observation? Is it the involvement of a conscious mind? Or is it simply an inherent, unexplained aspect of the quantum world? The mechanism of collapse itself remained a thorny, unresolved issue, often leading to philosophical debates about the role of consciousness in reality. This is precisely where the many worlds interpretation, MWI, first proposed by Hugh Everett III in 1957, steps in with a truly revolutionary idea. The wave function never actually collapses. Instead, every time a quantum measurement or interaction occurs, the universe doesn't choose one outcome and discard the others. Rather, the universe splits or branches into multiple parallel universes, with each universe representing one of the possible outcomes. Let's re-examine the double-slit experiment through the lens of MWI. When an electron is fired at the two slits, it doesn't choose one path. Instead, the universe splits into two branches. In one branch, the electron goes through the left slit, and in the other, an equally real universe, a copy of the electron goes through the right slit. And this happens for every electron, every quantum particle. Each possible path, each possible outcome, is actualized in its own distinct parallel universe. Now extend this to your own experience. Imagine you're about to flip a coin. Before you flip it, the coin is in a superposition of heads and tails. According to MWI, the moment the coin lands and you observe it, the universe branches. In one universe, you see heads. In another, equally real universe, a copy of you sees tails. Both outcomes are equally valid, and both are realized. You, the observer, don't experience a collapse. You simply find yourself in one of the resultant branches. And this branching isn't just for coin flips. It's happening constantly, for every quantum interaction, at every moment, everywhere in the universe. The very atoms in your brain, the firing of neurons, the absorption of photons by your eyes, all these are quantum events, constantly causing the universe to branch into countless, infinitesimally different parallel realities. This means that there are not just distant cosmic repetitions of you, level 1 multiverse, or universes with different physical laws, level 2 multiverse. According to MWI, there are infinitely many versions of you, each inhabiting a slightly different or profoundly different branch of reality. Every decision you've ever made, every choice you've ever contemplated, is played out by a version of you in some parallel universe. If you chose coffee this morning, a version of you chose tea. If you turned left instead of right, a version of you took that path. If you hesitated for a fraction of a second, a version of you didn't. All these possibilities, no matter how trivial or monumental, are actualized somewhere in the vast quantum multiverse. The beauty of the MWI, for its proponents, lies in its elegance. It avoids the need for a mysterious collapse mechanism. The wave function, the mathematical description of quantum possibilities, always evolves deterministically, never collapsing. The apparent collapse is merely a consequence of our subjective experience, of our being confined to one particular branch of the ever-expanding quantum tree. It solves the measurement problem by simply denying that there is a collapse in an objective sense. Instead, all possibilities are realized, and we merely experience one of them. However, the MWI also presents profound philosophical challenges and often sparks intense debate. If there are infinite versions of you, what does that mean for your individuality, your identity, or your free will? If every possible outcome is realized in some universe, does your choice truly matter? Proponents argue that the you who makes a choice is still the you in that particular branch, and your experiences are unique to that branch. Critics often find the sheer extravagance of an infinite number of parallel universes to be scientifically unparsimonious. Why postulate so many realities, if one will suffice? They argue that without a way to interact with these other branches, the MWI remains untestable in a conventional sense. But the unobservability of these branches is precisely what makes the MWI so hard to disprove. If each branching event leads to distinct, non-interacting universes, then by definition, we can never cross over into another branch or receive information from it. We are eternally confined to our own, constantly splitting branch of reality. This is why the analogy of a tree is often used. Once a branch splits, it continues to grow independently, never merging back with another branch. The different versions of you are causally disconnected. Despite its conceptual difficulties, the MWI is consistent with all experimental results of quantum mechanics. It is a mathematically sound interpretation that offers a coherent way to understand phenomena like superposition and entanglement without invoking arbitrary mechanisms. For instance, entanglement within the MWI means that the linked particles are actually parts of a larger quantum state that splits. When you measure one particle, the entire entangled system splits into multiple branches, each representing a correlated outcome. The instantaneous correlation across vast distances is explained not by communication, but by the fact that the two particles were never truly independent, but rather part of a larger branching quantum reality. They are merely realizing their pre-existing shared state in different branches of the universe. The MWI also provides a compelling, if unsettling, perspective on cosmic fine-tuning. If every possible quantum outcome is realized, and the universe has evolved through countless quantum interactions since the Big Bang, then it becomes inevitable that among the infinite branches there would be universes with the precise conditions for life to emerge. It's not just that our universe is lucky, but that our specific branch of the quantum multiverse happens to be one where life can exist. The other branches, where slight quantum variations led to different outcomes, might be barren or fundamentally different. The ongoing debate surrounding the MWI underscores a deeper point. Our fundamental understanding of reality at the quantum level is still incomplete. While quantum mechanics provides an incredibly accurate predictive framework, its interpretations grapple with the profound philosophical implications of its counterintuitive nature. The MWI is one of the boldest attempts to resolve these issues by postulating a constantly proliferating multitude of realities. Consider the thought experiment known as Schrödinger's cat, which dramatically illustrates the bizarre nature of quantum superposition and the implications for collapse or branching. Imagine a cat in a sealed box, along with a radioactive source, a Geiger counter, a hammer, and a vial of poison. The radioactive source has a 50% chance of decaying in an hour. If it decays, the Geiger counter detects it, triggers the hammer, smashes the vial, and the cat dies. If it doesn't decay, the cat lives. According to standard quantum mechanics, until someone opens the box and observes the system, the radioactive atom is in a superposition of decayed and undecayed states. This implies, unsettlingly, that the cat is also in a superposition, simultaneously both dead and alive inside the box. When you open the box, the wave function collapses, and you see either a dead cat or a live cat. The MWI offers a different solution. When the radioactive atom decays or doesn't decay, the universe branches. In one branch, the atom decays, the hammer falls, the poison is released, and the cat is dead. In another, equally real branch, the atom does not decay, and the cat lives. When you open the box, your consciousness also splits. One version of you experiences the dead cat reality, and another experiences the living cat reality. Both outcomes have occurred, each in its own distinct parallel universe. There is no dead and alive cat. There are two cats, one dead in one universe, one alive in another. This interpretation neatly avoids the spooky notion of a cat being simultaneously dead and alive, but at the cost of a constantly branching cosmic tree. The concept of identity within the MWI also becomes deeply intriguing. If there are countless versions of you, splitting off with every quantum choice, which one is the real you? From the perspective of the MWI, all of them are. Your conscious experience is simply located within one specific branch. The feeling of continuity you have is a subjective experience arising from the uninterrupted sequence of quantum measurements and decisions within your particular branch. There's no single master consciousness. Rather, consciousness is a phenomenon that is continually duplicated and diverges across the branching realities. While the many worlds interpretation offers a compelling deterministic resolution to the probabilistic nature of quantum mechanics, it also pushes the boundaries of our imagination about what constitutes reality. It challenges our intuitive sense of a singular, objective world. If this interpretation holds true, then reality is not a single path, but an ever-expanding multi-branched river of possibilities, with each current representing a distinct universe. Our perception, our consciousness, is merely riding one of those currents, experiencing a linear progression of events, while an infinite symphony of other realities plays out simultaneously, yet unreachably, alongside our own. This profound branching of reality has direct implications for our earlier discussions. If the universe is infinitely large and also constantly branching, level 3, then the sheer number of universes becomes astronomically vast. And if these branches can also arise within a larger multiverse of bubble universes, level 2, the complexity and scale become almost unfathomable. The interconnectedness of these ideas begins to paint a picture of a reality far richer and more complex than any single scientific theory could describe on its own. The ongoing scientific and philosophical exploration of the many worlds interpretation continues to drive new research in quantum information theory, quantum computing, and even foundational physics. While direct experimental verification of parallel universes remains a monumental challenge, the consistency and elegance of the MWI, combined with its ability to explain otherwise perplexing quantum phenomena, ensures its prominent place in the ongoing quest to understand the ultimate nature of reality. As we move beyond the bizarre branching of the quantum multiverse, we are compelled to ask, if reality can be so vast, so varied, and so multiplicitous in its quantum manifestations, could there be other dimensions, entirely different ways for space and time to exist, that are simply hidden from our perception? Could these unseen dimensions be the very pathways connecting some of these parallel realities, or simply represent additional layers of existence within our own? The next chapter will explore these tantalizing possibilities, inviting us to consider the idea of dimensions beyond our 3 spatial dimensions, a concept that stretches the very fabric of our imagination and offers another powerful lens through which to view the astonishing tapestry of reality. Our ongoing expedition into the multifaceted nature of reality has traversed the enigmatic realms of quantum weirdness and the mind-boggling implications of a vast, expanding, and potentially multi-branch cosmos. We've seen how particles defy classical logic and how entire universes might be constantly splitting or bubbling into existence. Now prepare to stretch your imagination in an entirely new direction, to dimensions beyond our familiar 3. What if the reality we perceive, with its length, width, and height, is merely a slice of a larger, more intricate spatial tapestry? What if there are other dimensions curled up too tightly to see, or existing in ways that defy our direct sensory experience? This chapter will explore the tantalizing possibility of dimensions beyond our sight, a concept that emerges from some of the most advanced and ambitious theories in modern physics. For centuries, our understanding of space was firmly rooted in 3 dimensions. We instinctively perceive the world in terms of up and down, left and right, and forward and backward. These 3 spatial dimensions, combined with the dimension of time, form the 4-dimensional space-time continuum that serves as the backdrop for our classical understanding of the universe. When we described Einstein's general relativity, we visualized this space-time as a flexible fabric, bending and warping under the influence of mass and energy. But what if this fabric has more threads, more layers, more fundamental axes than we can directly sense or move through? The idea of higher dimensions is not a recent invention of science fiction, though it often inspires it. It has a rich history in mathematics and theoretical physics. As early as the 1920s, mathematicians Theodore Kaluza and Oscar Klein independently proposed that our universe might contain a hidden, extra-spatial dimension. Their motivation was astonishingly elegant. If you added a tiny, curled-up fifth dimension to Einstein's general relativity, the equations naturally yielded not only gravity, but also the equations for electromagnetism, the force that governs light, electricity, and magnetism. It was a beautiful unification of two fundamental forces of nature. The reason we don't perceive this fifth dimension, they suggested, is that it is compactified or curled up into an incredibly tiny, unobservable loop at every point in our familiar three-dimensional space. Imagine a garden hose. From a distance, it looks like a one-dimensional line. An ant crawling along its length only perceives one dimension, forward or backward. But if you zoom in, you see that the surface of the hose actually has a second dimension around its circumference. The ant can move around the hose as well as along its length. For us, at our macroscopic scale, the circumference of this extra dimension is simply too small to perceive, so our reality appears three-dimensional. Kaluza and Klein hypothesized that our universe might have similar, incredibly tiny, curled-up dimensions at every point. This was a revolutionary idea, suggesting that our perceived reality is merely a projection or a larger-scale view of a more complex underlying structure. While Kaluza-Klein theory was a pioneering attempt at unification, it didn't quite fit all the experimental data regarding particle physics. However, the idea of extra dimensions resurfaced much more powerfully with the advent of string theory in the 1980s and its later extension, M theory, in the 1990s. These theories are arguably the most ambitious attempts in modern physics to unify all the fundamental forces of nature, including gravity, with quantum mechanics, essentially to find a theory of everything. String theory proposes that the most fundamental building blocks of the universe are not point-like particles, but tiny, one-dimensional vibrating strings of energy, unimaginably smaller than even an electron. Just as different vibrations of a violin string produce different musical notes, different vibration patterns of these fundamental strings produce different types of particles: electrons, quarks, photons, gravitons, the hypothetical particle of gravity, and so on. The beauty of string theory is that it naturally incorporates gravity, something that quantum mechanics struggles to do. However, for string theory to be mathematically consistent, it requires the universe to have more than 3 spatial dimensions. In fact, the most common versions of string theory require 10 or 11 dimensions, 9 or 10 spatial dimensions, plus 1 dimension of time. This is a staggering proposition. Our universe would exist not just as 3 spatial dimensions, but as a structure with many more. So, where are these extra dimensions? Just like in Kaluza-Klein theory, string theorists propose that these extra dimensions are compactified or curled up into incredibly tiny shapes at every point in our familiar 3-dimensional space. Imagine, at every single point in the universe, a tiny, intricate, multidimensional shape exists, far smaller than any atom, any nucleus, any particle. These shapes, known as Calabi-Yau manifolds in some versions of string theory, are complex, high-dimensional geometries. The way these extra dimensions are curled up, their specific geometric configuration, dictates the fundamental physical constants and the laws of physics that we observe in our macroscopic 3-dimensional world. It's as if the very rules of our reality are encoded in the hidden geometry of these tiny extra dimensions. Think of it this way. The laws of physics we observe are like the instructions written on the surface of a giant, complex, origami-like structure. We only see the unfolded, 3-dimensional paper, but the true nature of the instructions is encoded in the hidden folds and creases that are too small for us to detect directly. If the extra dimensions were curled up differently, our universe would have different physical laws. Perhaps gravity would be stronger, or the electron would have a different mass. This offers a profound potential explanation for the fine-tuning problem we discussed earlier. The seemingly just right values of our physical constants might simply be a consequence of the specific way these extra dimensions are curled up in our particular region of the multiverse. The implications of these curled up dimensions are profound. It suggests that our universe is much richer and more intricate than we perceive. While we cannot move through these extra dimensions because they are too small to navigate, their existence subtly influences the particles and forces that we do observe. For instance, the specific types of particles that exist, their masses, and the strengths of the fundamental forces are all thought to be derived from the specific geometry of these compactified dimensions. It's like hearing a piece of music and knowing there are instruments playing that you can't see, but whose presence shapes the sound you hear. However, the idea of extra dimensions isn't limited to these curled-up scenarios. More recently, some theories have proposed the existence of large extra dimensions, or brand world scenarios. In these models, our entire three-dimensional universe is thought to be a brane, a higher dimensional membrane, embedded within a larger, higher dimensional space called the bulk. Imagine our universe as a flat sheet of paper floating in a much larger multi-dimensional room. We, and all the particles and forces we interact with, like electromagnetism, the strong and weak nuclear forces, are confined to this sheet. But gravity, unlike the other forces, is hypothesized to be able to leak or propagate into the extra dimensions of the bulk. This could explain why gravity is so much weaker than the other fundamental forces. If gravity is spread out across these extra dimensions, its strength would be diluted in our familiar 3 dimensions. This model suggests that while we are stuck on our brane, there could be other branes, other universes, perhaps even parallel to our own, existing in the same bulk, just separated by an extra dimension that we cannot directly perceive or cross. This brane world concept offers intriguing possibilities for the multiverse. Our universe might not just be one bubble among many, level 2 multiverse, but one brane among many, floating in a higher dimensional bulk. These other branes could be other universes, perhaps just millimeters away in a hidden dimension, yet entirely unreachable. This opens up the possibility of a level 5 multiverse, which is less about different initial conditions or quantum branches, and more about different slices of reality existing within a higher dimensional space. The existence of these large extra dimensions could also offer solutions to other puzzles in physics, such as the hierarchy problem, why gravity is so much weaker than other forces. While these extra dimensions are currently theoretical, physicists are actively searching for indirect evidence of their existence. One line of research involves precision measurements of gravity at very small distances. If gravity truly leaks into extra dimensions, its strength might deviate from the inverse square law, which applies in 3 dimensions, at very tiny scales, becoming stronger than expected. Experiments are constantly pushing the limits of measurement, looking for these subtle deviations. Another approach involves searching for mini black holes that could be formed in powerful particle accelerators, like the Large Hadron Collider. If extra dimensions exist, the energy required to create these black holes would be lower, making their formation more plausible. If detected, it would be a powerful though indirect signature of extra dimensions. The concept of higher dimensions profoundly impacts our understanding of reality. It means that the universe we perceive is not the whole story. It's like living in a 2-dimensional world, a flat drawing on a piece of paper, and suddenly realizing that there's a 3rd dimension, height, that you can't see, but that allows for a whole new level of complexity and connection. These extra dimensions could provide the missing pieces to unify our theories of gravity and quantum mechanics, to explain the fundamental constants of our universe, and even to offer new pathways for understanding the vastness and interconnectedness of the multiverse. They suggest that what appears as empty space to us might in fact be intricately folded or multi-layered, teeming with hidden geometric structures that define the very nature of existence. Embracing the idea of higher dimensions requires a radical shift in perspective. It challenges our deep-seated intuition about the fundamental nature of space. It moves us beyond simply conceiving of length, width, and height as the only possibilities for spatial existence. Instead, it invites us to imagine a reality that is topologically richer, with unseen pathways and unperceived directions that shape our familiar world in subtle yet profound ways. These hidden dimensions could be the cosmic wiring that connects different universes in the multiverse, or simply represent the fundamental geometry that gives rise to the physical laws we observe. The search for these extra dimensions is one of the most exciting frontiers in theoretical physics. It pushes the boundaries of our mathematical understanding and inspires cutting-edge experiments, whether they are infinitesimally curled up or constitute a larger bulk that our universe is embedded within. The possibility of dimensions beyond our three spatial dimensions paints a picture of reality that is far more expansive and intricate than we can currently grasp. It prepares us for an even more profound shift, one that questions the very nature of our perceived reality itself, asking whether our entire universe and everything within it might not be physical at all, but rather a sophisticated construct. If reality can have more dimensions, could it also be an elaborate simulation? That is the next fascinating and perhaps unsettling question we will explore. Now we confront perhaps the most existentially disquieting possibility of all, one that questions the very foundation of our perceived reality. Are we living in a computer program? The simulated realities hypothesis. This isn't a new concept born solely from the digital age. Philosophers throughout history have pondered whether our perceived reality might be an illusion, a dream, or a grand deception. Plato's allegory of the cave, ancient Hindu philosophies like Maya, and René Descartes' evil demon thought experiment all touch upon the profound uncertainty of what is truly real versus what is merely perceived. However, in our modern era, with the breathtaking advances in computing power, virtual reality, and artificial intelligence, this age-old philosophical question has taken on a startlingly new and scientifically plausible dimension. The question is no longer merely, is reality an illusion? But could our reality literally be a sophisticated computer simulation, indistinguishable from the base reality in which it is running? This idea, known as the simulation hypothesis, gained significant traction with a compelling argument put forth by philosopher Nick Bostrom in 2003. Bostrom proposed a trilemma, suggesting that at least one of three propositions must be true. First, that virtually all civilizations at our technological level or below go extinct before becoming post-human, before they develop the enormous computing power necessary to run highly detailed simulations of their ancestors. This is a rather bleak outlook, suggesting a great filter ahead of us that prevents advanced civilizations from emerging. Second, that any post-human civilization that does emerge loses interest in running ancestor simulations. Perhaps they deem it unethical, uninteresting, or too complex to manage. This seems less likely given human curiosity and the historical progression of technological development. Third, and this is the intriguing one, that we are almost certainly living in a computer simulation. If a post-human civilization achieves vast computational power capable of simulating entire universes with conscious beings, and if they have even a slight interest in doing so, then the number of simulated realities they could create would vastly outnumber the single base reality from which they originated. If you can simulate thousands, millions, or even billions of universes, the statistical probability of any given conscious entity, like you or me, residing in the original base reality becomes infinitesimally small. It's far more likely, mathematically, that we are one of the simulated minds in one of those simulated realities. To grasp the staggering implications of this, consider the trajectory of computing power. In just a few decades, we have gone from rudimentary calculators to supercomputers capable of performing quadrillions of calculations per second. We are already developing sophisticated virtual reality environments that engage multiple senses and artificial intelligence that can mimic human conversation and creativity. Imagine what computing power will be like in a few centuries or millennia. It's not unreasonable to extrapolate that a sufficiently advanced civilization could develop computers capable of simulating entire universes down to the atomic or even quantum level, complete with conscious inhabitants. If our universe is truly just a vast collection of fundamental particles interacting according to physical laws, then in principle those interactions could be digitally replicated if enough computational resources were available. The very laws of physics, the mathematical elegance we admire in the cosmos, could be seen as the underlying code of a grand program. The fundamental constants, like the speed of light or the gravitational constant, might be parameters set in the simulation's initial conditions. The seemingly random probabilistic nature of quantum mechanics could be a computational shortcut, a way for the simulation to save processing power by not rendering every single quantum event until it needs to be observed. Much like a video game engine only renders the details of a scene that are actively being viewed by the player. Think back to the observer effect in quantum mechanics, where the act of measurement seems to force a particle into a definite state from a superposition of possibilities. In a simulation, this could simply be when the program renders the specific outcome that needs to be displayed to the simulated observer. If our reality were a simulation, it would explain some perplexing cosmic observations. The fine-tuning of our universe, where the physical constants are perfectly balanced for the emergence of life, could be explained by a simulator deliberately setting those parameters to allow for interesting outcomes, like the development of conscious civilizations. It wouldn't be a cosmic coincidence, it would be a design choice. The vast emptiness of space, the apparent lack of extraterrestrial life, the Fermi paradox, could be a feature of the simulation, perhaps to manage computational resources, or to allow for a more controlled experiment. Or perhaps the simulator hasn't filled in the rest of the galaxy yet. Furthermore, anomalies in the universe, seemingly inexplicable phenomena, could be bugs in the code or glitches in the rendering. Perhaps unexpected phenomena in high-energy physics or subtle deviations from expected cosmological models could be hints of computational limits or unexpected features of the underlying program. Some even speculate that phenomena like dark matter and dark energy, which make up about 95% of the universe's energy content but remain mysterious, could be manifestations of the simulation's underlying architecture or energy budget. However, the simulation hypothesis faces significant challenges and criticisms. One of the primary criticisms is its unfalsifiability. If our reality is truly a simulation, how could we ever prove it? Any experiment we perform, any observation we make, would itself be part of the simulation, and the simulated laws of physics would hold true within it. It's a self-contained system. If the simulator is sufficiently advanced, they could always hide any evidence of the simulation from within. This makes it difficult to consider it a scientific hypothesis in the traditional sense, as it doesn't offer clear, testable predictions that could prove it false. Another line of criticism focuses on the immense computational resources required. Running an entire universe down to the quantum level, with billions of conscious beings, would require processing power that seems to defy the imagination, even for a post-human civilization. However, proponents argue that our understanding of future computing is limited. Perhaps there are unknown fundamental limits to computation, or perhaps the simulation doesn't need to render every detail at every moment. It could be a lazy simulation, only rendering what is necessary for the simulated conscious beings to experience. The very concept of consciousness within a simulation also raises deep questions. If our brains are merely complex algorithms within a program, are we truly conscious, or are we just sophisticated automatons? The simulation hypothesis doesn't necessarily dictate that consciousness is an illusion, but rather that its substrate is digital rather than purely physical in the base reality. If a simulation is sufficiently detailed and realistic, then the simulated consciousness within it would be just as real to itself as our consciousness is to us. For the simulated beings, their reality is real. Consider the ethical implications. If we discover we are living in a simulation, what are our responsibilities? Do we have a duty to the simulator? Do we try to communicate with them? And if we become advanced enough to create such simulations, do we have ethical obligations to the simulated beings within them? These are not merely philosophical ponderings, but potentially practical questions for humanity's far future. The simulation hypothesis connects to other areas of our reality exploration. If there are multiple universes, the multiverse, then it's plausible that some of them are simulated universes. In a level 2 multiverse, where different bubble universes have different physical laws, some might be natural while others are simulated. In a level 4 multiverse, where all mathematically consistent realities exist, a simulated universe could be just one such mathematically consistent structure. The simulation hypothesis offers a powerful, unifying explanation for phenomena like fine-tuning, cosmic anomalies, and the apparent lack of extraterrestrial contact, but it does so by introducing an external, unobservable meta-reality where the simulation is running. Despite the challenges, the simulation hypothesis remains a fascinating and thought-provoking idea. It forces us to question our assumptions about what is real and to consider the limits of our perception. It encourages us to look for subtle tells in our universe that might betray its simulated nature. Mathematical regularities, logical inconsistencies, or computational artifacts. Some physicists even propose that the very pixelation of space at the Planck length, the smallest theoretically meaningful unit of length, could be a sign of a digital rendering limit. The discrete nature of quantum mechanics, where properties jump rather than being continuous, also finds a natural parallel in digital computation. Ultimately, whether we are living in a simulation or not, the hypothesis serves as a powerful intellectual tool. It forces us to rigorously examine the nature of our reality, to look for inconsistencies, and to push the boundaries of scientific inquiry. It highlights the profound questions that arise when we combine advanced physics with cutting-edge computational science and philosophy. It reminds us that our common-sense understanding of reality is continuously challenged by new scientific discoveries and theoretical frameworks. From the quantum foam to the expanding cosmos, from hidden dimensions to the possibility of a grand cosmic program, our journey has peeled back layer after layer of perceived reality. We've seen how our senses construct our world, how particles dance in probabilistic clouds, how space and time bend and warp, and how other universes might exist beyond our grasp. The simulated reality hypothesis offers a radical reinterpretation of all these observations, suggesting that they might simply be the meticulously crafted rules and visuals of an advanced computational environment. This leads us to the most profound and intimate question of all. If reality itself can be so fluid, so uncertain, so vast, and potentially simulated, what then is the role of our own consciousness? How does our mind perceive, interpret, and perhaps even shape this elusive thing we call reality? That will be the focus of our next and deeply introspective chapter. We have moved from the familiar solidity of our everyday world to the probabilistic dance of quantum particles, to the stretching and bending of space-time, into the vastness of potentially infinite universes, and even considered the unsettling possibility that our entire cosmos might be a sophisticated computer simulation. Each step has chipped away at our preconceived notions, revealing that what we perceive as real is far more fluid and mysterious than we ever imagined. Now we turn our attention inward, to perhaps the most intimate and equally enigmatic aspect of reality, the nature of consciousness, how our minds shape reality. Throughout our exploration, a recurring theme has emerged: the role of the observer. In the quantum realm, the act of measurement seems to collapse a particle's probabilistic existence into a definite state. In the context of the multiverse, particularly the many worlds interpretation, our consciousness is seen as branching along with the universe, experiencing just one of an infinite number of parallel realities. And in the simulation hypothesis, our very minds could be sophisticated algorithms running within a cosmic program. In all these scenarios, the presence of a conscious mind seems to play a peculiar, perhaps even fundamental role in defining or experiencing reality. But what is consciousness? How does it arise from the wet, squishy matter of the brain? And what is its true relationship to the universe it perceives? For centuries, consciousness has been the exclusive domain of philosophy and religion, a deeply personal and subjective experience, often deemed beyond the reach of scientific inquiry. We all know what it feels like to be conscious: the vivid colors of a sunset, the pang of hunger, the joy of a melody, the memory of a cherished moment, the internal monologue of our thoughts. This subjective, first-person experience, what philosophers call qualia, is incredibly rich and complex. It's the what it's like to be you. But how does a collection of neurons firing electrical impulses and exchanging chemical signals, give rise to this internal world of feeling, thought, and awareness. This is famously known as the hard problem of consciousness, coined by philosopher David Chalmers. The easy problems are about explaining brain functions, like memory, attention, and sensory processing. The hard problem, however, is about explaining why these physical processes produce subjective, qualitative experience at all. Why isn't it all just electrochemical activity without an internal, felt reality? Traditional scientific materialism often approaches consciousness as an emergent property of the brain. Just as the intricate interactions of countless molecules in a hurricane give rise to a complex weather system, the incredibly complex network of billions of neurons and trillions of connections in the brain is thought to somehow give rise to consciousness. Neuroscientists have made tremendous strides in identifying the neural correlates of consciousness, specific brain regions and patterns of activity that are associated with conscious experience. For example, activity in certain areas of the visual cortex is linked to conscious sight, and damage to specific brain structures can impair or alter consciousness. This view suggests that consciousness is entirely a product of the brain, a biological phenomenon that arises when neural complexity reaches a certain threshold. However, this emergent view struggles with the hard problem. It can describe what the brain does when we are conscious, but not why we have the subjective experience of consciousness itself. It's like describing the intricate workings of a clock without explaining why it tells time. This has led some scientists and philosophers to propose more radical ideas about consciousness, suggesting it might not merely be a byproduct of the brain, but something more fundamental, perhaps even intimately connected to the fabric of reality itself. One such idea is that consciousness, or at least the potential for consciousness, is a fundamental property of the universe, much like mass or charge. This is a concept often explored within panpsychism, the view that consciousness, or proto-consciousness, is ubiquitous, present in rudimentary forms, even at the most basic levels of reality, perhaps even in individual particles. This doesn't mean that an electron is conscious in the way a human is, but that it possesses some infinitesimally small, irreducible element of experience, or information processing, that when combined in sufficiently complex ways, gives rise to the richer forms of consciousness we observe in living beings. While speculative, panpsychism offers a way to bridge the gap between the physical and the subjective, suggesting that consciousness isn't something that magically emerges at a certain level of complexity, but rather scales up from fundamental properties of matter. Another intriguing avenue of thought explores the potential connections between consciousness and the quantum realm. We've discussed the observer effect, where the act of measurement seemingly forces a quantum particle to choose a definite state from a superposition of possibilities. Some interpretations of quantum mechanics, particularly older ones, explicitly link this collapse to the presence of a conscious observer, while most modern physicists prefer interpretations that don't require human consciousness for collapse, e.g. the many worlds interpretation, or objective collapse theories that suggest collapse is a fundamental, observer-independent process. The lingering mystery of the observer effect continues to fuel speculation about a deeper link between mind and matter. For instance, some theories propose that the brain itself might operate on quantum principles, that consciousness is not merely a classical computation, but involves subtle quantum processes. The orchestrated objective reduction or theory, proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggests that consciousness arises from quantum computations occurring in microtubules within neurons. While highly controversial and not widely accepted in the neuroscience community, such theories attempt to directly bridge the gap between the bizarre rules of the quantum world and the enigma of consciousness. They speculate that the very indeterminacy and superposition inherent in quantum mechanics might be essential for the richness and unpredictability of conscious experience. If this were true, it would mean that consciousness isn't just affected by quantum reality. It might actively participate in shaping it, in that profound moment of wave function collapse. The relationship between consciousness and time is also a fascinating area of inquiry. Our conscious experience of time is linear, We move from past to present to future. But as we learned from general relativity, time is relative. It slows down or speeds up, depending on motion and gravity. And in the theoretical block universe view, often arising from general relativity, all moments in time, past, present, and future, are equally real and exist simultaneously, much like different frames in a film reel that all exist at once, even though we perceive them sequentially. If this block universe is true, then our linear experience of time is an illusion, a trick of consciousness. Why do we experience time as flowing forward, and why do we only perceive one now? Could consciousness be the mechanism that slices through this eternal block, creating our subjective experience of a flowing present? Furthermore, consider the implications of the simulation hypothesis on consciousness. If our reality is a simulation, then our conscious minds are, in essence, algorithms or complex software running within that simulation. Are we truly conscious, or are we just incredibly sophisticated programs? From an internal, subjective perspective, it makes no difference. The feeling of being you, of experiencing the world, is just as real within the simulation as it would be in a base reality. This raises profound questions about the nature of artificial intelligence and artificial consciousness. If we can create sufficiently advanced simulations of brains, would those simulated brains become conscious? The simulation hypothesis suggests that if we can simulate a conscious entity, then simulated consciousness is just as valid as organic consciousness. This challenges our anthropocentric view of consciousness, forcing us to consider that intelligent, feeling beings might exist in vastly different forms and substrates than our own. The role of consciousness in defining our reality extends beyond these scientific and philosophical debates into our everyday lives. Our consciousness not only interprets sensory data, but it also actively filters and constructs our perception. As we briefly touched upon in Chapter 1, our minds are not passive receivers of objective truth. They are active constructors. Our memories, our emotions, our expectations, our biases, all these profoundly influence what we see and hear and feel. The phenomenon of selective attention is a prime example. In a crowded room, you can consciously focus on a single conversation, effectively tuning out dozens of others. The sounds are physically present, but your consciousness chooses what to foreground and what to suppress. This active filtering means that our perceived reality is always a personalized, subjective experience. Consider the placebo effect, where a patient experiences real physiological improvement simply because they believe they are receiving a beneficial treatment, even if it's inert. This powerful phenomenon demonstrates how the mind, through belief and expectation, can literally influence the body and its experience of reality. Conversely, the nocebo effect shows how negative expectations can cause real harm. Our conscious and subconscious beliefs can shape our physical and mental experience of the world in profound ways. The relationship between consciousness and reality also touches upon spiritual and mystical traditions. Many ancient philosophies and religions posit that consciousness is not merely a product of the brain, but is fundamental to the universe, perhaps even the source of reality. Ideas like a universal consciousness, or the concept that all existence is a manifestation of a cosmic mind, resonate with some of the more radical interpretations emerging from modern physics and philosophy. While these are often outside the realm of empirical science, they highlight the enduring human quest to understand consciousness and its place in the cosmos. Ultimately, the nature of consciousness remains one of the greatest unsolved mysteries. We know it exists because we experience it directly. We know it is intimately tied to the brain, as brain damage can alter or extinguish it. But the hard problem persists. Why does electrochemical activity produce subjective experience? And what is the precise relationship between this subjective experience and the objective, external reality that science seeks to describe? Perhaps consciousness is not merely an observer of reality, but an active participant in its very unfolding. Perhaps it is not just a passenger on the train of reality, but somehow helps to lay the tracks. If the quantum world is intrinsically probabilistic until observed, and if our universe is just one of many branches arising from quantum choices, then consciousness might be the very mechanism by which definite realities are selected or experienced from a sea of possibilities. The implications of this intimate connection between consciousness and reality are immense. It transforms us from passive recipients of a predetermined universe into active co-creators of our experienced world. It suggests that our minds are not merely confined within our skulls, but are perhaps intrinsically linked to the very fabric of the cosmos, playing a role in its definition and manifestation. This idea is perhaps the most profound shift in perspective that our journey through reality is offered. It compels us to look inward as deeply as we have looked outward, understanding that the greatest mysteries of the universe might reside not only in the distant galaxies or the subatomic realm, but within the very essence of our own conscious being. As we conclude our exploration of the different realities of the universe, having traversed the quantum, the cosmic, the theoretical, and the simulated, we arrive at a vantage point where all these threads converge. The universe is not singular, but multifold. It is not static, but dynamic. It is not always what it seems, but is often a product of filters, interpretations, and perhaps even conscious participation. Our final chapter will synthesize these astonishing insights, offering a renewed understanding of what it means to exist within such a rich, mysterious, and endlessly fascinating cosmos, inviting a sense of wonder and humility about the boundless unknowns that still await discovery, Our odyssey through the multifaceted nature of reality reaches its culminating chapter. We have journeyed from the seemingly solid ground of our everyday perception, delving into the elusive dance of quantum particles, feeling the stretching and bending of space-time itself, gazing out at the potentially infinite expanse of the multiverse, peering into the unsettling possibility of simulated realities, and finally, turning inward to ponder the mysterious nature of consciousness and its profound role in shaping our experience of existence. Each revelation has been a layer peeled back, exposing a universe far more intricate, mysterious, and alive than any single static view could ever convey. Now we bring these threads together to synthesize these astonishing insights into a coherent, yet open-ended understanding of existence, and to embrace the boundless unknowns that still await discovery. This is embracing the unknown, a new understanding of existence. Throughout this audiobook, we have repeatedly challenged the notion of a single, monolithic reality. We began by questioning the very solidity of the chair you might be sitting on, revealing it as a teeming cloud of quantum probabilities rather than an unmoving, definite object. This initial shift from certainty to probability, from solidity to energetic fields, was our first step in dismantling the comfortable yet limited worldview of classical physics. The quantum realm, with its superposition, entanglement, and the perplexing observer effect, taught us that at the most fundamental level, the universe is inherently fuzzy, indeterminate until measured, and profoundly interconnected in ways that defy our classical intuitions of space and time. It suggested that observation is not a passive act, but an active participant in shaping what appears to be real. From the microcosm, we ascended to the macrocosm, exploring the revolutionary insights of Einstein's relativity. We discovered that space and time are not fixed, independent containers, but a single, malleable fabric, space-time, that bends and warps in the presence of mass and energy. This warping creates what we perceive as gravity, governing the dance of planets and the very evolution of galaxies. Time itself proved to be relative, speeding up or slowing down, depending on your motion or gravitational environment, dismantling the notion of a universal now. And on the largest scales, we saw that our universe is not static, but expanding, an ongoing cosmic inflation born from the Big Bang, stretching space itself and carrying galaxies ever further apart. This dynamic, expanding cosmos immediately opened the door to the staggering possibility of a vast, unobservable universe extending far beyond our cosmic horizon, where repetitions of our reality might exist due to sheer statistical probability in an infinite expanse. This concept of an unobservable and potentially infinite universe was merely the first whisper of the multiverse hypothesis. We then explored how our most robust cosmological theories, particularly eternal inflation, suggest that our universe is just one bubble in an infinite, constantly frothing ocean of space-time, each bubble potentially possessing its own unique set of physical laws and constants. This Level 2 multiverse offered a compelling resolution to the perplexing fine-tuning of our universe, suggesting that our specific laws are not a cosmic fluke, but simply the conditions necessary for life to emerge within a statistically inevitable range of possibilities. But the multiverse journey didn't stop there. We delved into the radical implications of the many worlds interpretation of quantum mechanics, where every quantum measurement, every probabilistic outcome, causes the universe to split into myriad parallel realities. Here, an infinite number of yous live out every conceivable possibility, every choice, creating a constantly branching cosmic tree. This Level 3 multiverse redefined our sense of personal existence, suggesting that reality is not a single linear path, but an ever-expanding tapestry of simultaneous actualizations. And finally, we touched upon the most abstract Level 4 multiverse, where every mathematically consistent universe exists, hinting that reality itself might be fundamentally mathematical in nature. The audacious leaps continued as we contemplated the simulation hypothesis, the possibility that our entire perceived reality, from the quantum foam to the furthest galaxy, could be a sophisticated computer program running on a supercomputer in a base reality. This hypothesis, though challenging to prove or disprove, forces us to rigorously question the nature of our empirical observations and to consider the profound implications of an existence that might be entirely a computational construct. It aligns surprisingly well with certain quantum phenomena, like the observer effect, and the discrete nature of reality at fundamental scales, perhaps hinting at computational shortcuts. Finally, we turned our gaze inward, recognizing that at the heart of all these diverse realities stands the enigma of consciousness. We explored the hard problem, how the physical brain gives rise to subjective experience, and considered radical ideas, from consciousness being a fundamental property of the universe, panpsychism, to its potential role in quantum wave function collapse. We acknowledge that our consciousness is not a passive mirror reflecting an objective world, but an active filter, interpreter, and even constructor of our personal reality, deeply influenced by our beliefs, expectations, and biological makeup. The very act of being aware might be the ultimate gateway to understanding the nature of reality itself, perhaps even playing a role in its manifestation. So what does this grand tour of diverse realities mean for you, the average person living your everyday life? It means that the universe is infinitely more fascinating than we often give it credit for. It means that science, far from diminishing wonder, amplifies it beyond measure. The questions we have explored are not abstract academic exercises. They are profound inquiries into the very nature of existence, our place within it, and the limits of human knowledge. The first crucial takeaway is to embrace uncertainty. Our journey has revealed that at its most fundamental levels, reality is not definite and fixed, but probabilistic and fluid. From quantum particles existing in multiple states simultaneously to the branching realities of the multiverse, determinism, the idea that everything is predetermined, has been profoundly challenged. This doesn't mean that anything goes or that reality is purely subjective. It means that the universe operates on deeper, more nuanced principles than simple cause and effect as we experience it at our macroscopic scale. It encourages a humility, an openness to possibilities that defy common sense, and a recognition that our understanding of reality is always evolving, always subject to revision in the face of new discoveries. Secondly, cultivate a sense of interconnectedness. The universe, at its deepest levels, appears to be a vast, intricately woven tapestry. Entangled particles across light years are intrinsically linked. Space-time connects all events. The very existence of multiple universes in the multiverse might imply a larger, unified framework from which they all emerge, and the possibility of consciousness being fundamental hints at a deeper unity between mind and matter. This perspective encourages us to look beyond individual phenomena and to seek patterns, relationships, and underlying unity in the seemingly disparate aspects of existence. Your existence is not isolated. It is a profound and intricate part of this cosmic web. Thirdly, recognize the power of perception and consciousness. While we haven't definitively answered the hard problem, we've seen how our senses construct our subjective reality, how our minds filter and interpret information, and how the act of observation plays a role in the quantum world. This underscores the active role you play in your own experience of reality. While objective laws of physics govern the universe, your unique conscious journey through it is an active process of interpretation and engagement. It suggests that paying attention to our inner world, to our biases, to our assumptions, is just as crucial as observing the external world. Finally, and perhaps most importantly, cherish the unknown. In an age where we often seek immediate answers and complete certainty, the universe continues to present us with profound mysteries: dark matter and dark energy, the nature of consciousness, the true origin of the Big Bang, the ultimate fate of the universe, and the definitive answers to the multiverse and simulation hypotheses. These are not solved problems. They are vibrant, active frontiers of scientific inquiry. The beauty of science is not just in the answers it provides, but in the relentless curiosity it fosters, the ever-deepening questions it compels us to ask. To embrace the unknown is to embrace the true spirit of discovery, to acknowledge that our current understanding is but a tiny island in a boundless ocean of knowledge. This new understanding of existence, therefore, isn't about giving you definitive answers to every question. Instead, it's about providing a framework for thinking about reality in a more expansive, nuanced, and wonder-filled way. It invites you to see beyond the obvious, to question the unquestioned, and to appreciate the astonishing complexity that underlies every moment of your existence. It's about recognizing that the greatest adventures are often those that lead us to the very edge of our comprehension. The scientific journey is an ongoing one. Every new discovery, every new theoretical breakthrough pushes the boundaries of our understanding, revealing even more layers of reality. Just as Einstein revolutionized Newton's clockwork universe and quantum mechanics shattered classical certainty, future discoveries will undoubtedly reshape our current views. New instruments, new experiments, and new theoretical frameworks will continue to unravel the cosmos's deepest secrets. We are living in an extraordinary time where humanity stands on the cusp of profound new insights into the nature of space, time, matter, energy, and consciousness itself. This audiobook is not an end, but a beginning. It is an invitation to carry these questions with you, to cultivate a perpetual sense of wonder, and to look at the world around you with new eyes, knowing that beneath the surface of the mundane lies an extraordinary, multidimensional, and perhaps infinitely diverse reality. The universe, in all its perplexing, beautiful, and awe-inspiring complexity, awaits your continued curiosity. The most exciting discoveries, the most profound answers, may still lie hidden, waiting for a questioning mind to uncover them. Embrace the journey, for the reality we inhabit is truly beyond imagination.